Super.
Definitely. Yeah. Once you make it full screen, I'm sure the call it does pick it up then.
Yeah.
Terrific.
Yeah,
So,
fine.
Can you mute all the microphones?
Yeah, mute all the microphones.
yep.
So
2, 2, 1, 2. Yeah. Hey. Hey, hey. Yeah, yeah. Hey, hey. 2, 2.
Good morning, everyone. It is now 10:30. We're supposed to start, but unfortunately, we still are missing 3 of the speakers. That's half of the speakers for the session. So I'm going to give it another few minutes with very high hopes. Okay, now. All right. Hello once again. Now we're only missing one speaker, so I say that's progress. So let's get started, and I will monitor once there is a speaker coming in. So let's cross fingers. So welcome to the second session on machine learning this week at PETS. We happen to have everybody presenting in person, so no recorded talks. And after the session, we will be rewarded with lunch. So I would say there are all the conditions to pay attention. So let's welcome our first speaker, Amir Hamid from University of Maryland, Baltimore County, who is a PhD candidate there. And he'll present the work on Gen AI PA Bench, a benchmark for generative AI-based privacy assistance. Welcome.
Good morning, everyone. I am Amir Hamid, and I'll be presenting my work on GenAI Bench, a benchmark for generative AI-based privacy assistance. Our focus is on evaluating whether large language models are a viable approach for analyzing and simplifying privacy policies. Giving some background about privacy policies and data regulations, privacy policies and data regulations are increasingly becoming complex and time-consuming to read. And there has been a lot of research in these domains, and research has found out that the length of these privacy documents quadrupled since 2000, and it's taking an average of 304 hours per year to read them. An average American adult can read at a grade level of 7th or 8th, while comprehending these privacy policies require at least college level understanding. 67% of the people don't understand what companies are doing with their data. And research also highlights that there is an increase in data collection and sharing, where there is a lack of choices in data practices. Traditional methods of analyzing privacy policies include manual analysis as well as automated tools. For example, study done by Mozilla, Privacy Not Included, which is a really highly informative study, but is too costly and time consuming. In 2022, Mozilla analyzed 260 products, and it took around 68,000 minutes to complete this evaluation, which is not viable for products at scale. Automated analysis using machine learning, deep learning, natural language processing, and knowledge graphs are highly effective, but there are certain challenges with them as well. As they are based on natural language processing, getting precise answers and understanding user questions become hard. Recently, large language models like ChatGPT-4 have emerged as a promising new approach, but their effectiveness remains to be thoroughly evaluated. Generative AIs, mainly large language models, excel at processing a large volume of text swiftly. They can enhance the accessibility of complex privacy documents, understanding context and intent behind user questions, as well as they can produce human-readable answers. So, combining the generative AI with a chatbot interface, we can create a privacy assistant which is capable of answering privacy-related questions. This innovation has the potential to make complex documents like privacy documents more understandable and user-friendly. Why is evaluation essential? Evaluation is essential because large language models tend to hallucinate. As an example in the figure in the top right, we can see that answering a general question, it can hallucinate. So evaluation becomes important. Evaluation also makes sure that the answers we are getting are accurate and concise. There have been a lot of studies done to evaluate the applications of these generative AI models. Recently, GPT-4 scored 710 out of 800 in SAT reading and writing section. Also in bar exam, GPT-4 scored 298 out of 400. So where is our exam in evaluating these Gen AIs in questioning question answers about privacy-related topics? So here, Gen AI Bench comes in. Gen AI Bench is a comprehensive benchmark which is able to evaluate these generative AIs in answering questions about privacy documents. There are 5 main important components of Gen AI Bench: privacy documents and questions, annotated answers, metrics, and evaluator tool. So we'll delve in each of them one by one. Privacy documents. Privacy documents include products like Twitter, Airbnb, Facebook, Uber, and Spotify. These privacy documents were sourced from their respective websites, and they were up to date at that time. Also, we include documents like GDPR and CCPA. Our benchmark includes a diverse range of privacy topics and real-world questions sourced from various platforms like Twitter, Reddit, and FAQs. It covers critical areas such as privacy by design innovations, user control, transparency, compliance and accountability, among others. We include 32 privacy questions as well as their paraphrase versions that are 96 in total. The paraphrase versions were generated using popular paraphrasing tool like Quillbot. We initially generated 10 questions for each of the privacy question, ultimately keeping 3, which match the meaning of the questions. The variety helps us thoroughly test the generative AI's ability to handle different types of privacy-related queries. We evaluate the generative AI based on key metrics such as relevance, accuracy, completeness, clarity, and reference. Our benchmark also includes over 200 plus expert annotated answers as a benchmark to ensure AI's responses are held to high standards. In the bottom left, we have a figure here where we see a query from the user and there is an answer. So there are different color highlights in the answer where green marks that the part of that answer was accurate. Yellow says that there may be some disparity with the answer, and red means that the referencing part was totally wrong. Coming to evaluator path, the Gen AI Bench evaluator automates prompt generation and execution, allowing us to systematically test the AI's performance across various scenarios. The evaluator can generate prompts with or without privacy documents, with segmented portions of the documents, as well as requesting the summary first. This automation provides us a robust assessment of generative AI's capabilities to ensure consistency in testing. We have conducted an extensive experiments with leading large language models like ChatGPT-4, Google Bard, and Bing AI. The experimentation date was from July to August 2023. So the analysis which we performed using Gen AI Bench are like quality of responses to privacy policy questions, robustness through paraphrase questions, ability to recall learned privacy policy knowledge, quality of responses to regulation questions, and quality of privacy policy summaries. So due to the time limitations, we'll delve in the first experiment, which is quality of the responses to privacy policy questions. In the x-axis, we see privacy policies, and on the y-axis, we see the scores. While these large language models generally performed well, their responses can be inconsistent. When good performance can be seen while executing the benchmark for multiple runs, but when we do it for some runs, the performance is really bad, less than 10 for some questions. As you can see here, highlighted in the red, in the Spotify privacy policies, some of the questions got answers which were less than 10. If we delve deep in the metrics for each of the chatbot, we see that answers were very clear and relevant for the models studied. But these models failed badly at referencing, and accuracy was sometimes a hit or a miss, highlighting the need for ongoing refinement and evaluation. These are some of the highlights from our study, which are generative AI systems struggle more with compliance and accountability topics. Policy length rather than reading level significantly affected system performance. Questions with explicitly defined content were easier for the systems to handle. Paraphrase questions reduced the system performance, highlighting the need for user-friendly queries. Systems scored higher on privacy regulations due to more online discussions compared to the specific privacy policies. In conclusion, I want to say generative AI offers potential for advanced privacy assistance, but need rigorous evaluation. GenAIPA Bench is the first benchmark for generative AI-based privacy assistance on privacy policies and regulations. Our current generative AI show promise but struggle with paraphrasing, reference, and accuracy. The artifacts are available on GitHub, and we plan to keep our benchmark updated. Thank you for your time and attention. I'm looking forward to answering any questions about our study. Thank you.
Let's thank Amir. Are there any questions about this study? Okay, I will get started then. Can you please clarify once more about how you compute accuracy? Do you have to manually cross-check with ground truth?
Yeah, so we have manually annotated answers. So we get the answers from GenAIPA, and then we compare the answers with the ground truth and come up with the score.
And the ground truth was composed by your research team?
Yeah.
Okay, thank you. And I was missing a bit the objectives of paraphrasing. Could you summarize that?
Paraphrasing was trying to mimic how diverse users ask the same question. So if I ask the one question, the same question can be asked by another user in a different way. So paraphrasing was important to address this issue.
So you only use it in your test set, or you also augment your training information with paraphrasing?
Yeah, this is for like the answering. It's not test, and evaluation is just like...
so there's no fine-tuning on paraphrased questions. Okay, thank you. Are there any questions to Amir in the meantime?
Thank you. So I had a question also related to verifying and to the accuracy, and I'm wondering, I can imagine that several privacy policies are sometimes vague or ambiguous or missing some information, and I'm wondering to which extent did you encounter that as an issue, that it's not really possible to answer some questions, and how do you deal with these types of queries about the privacy policy?
So we had some experiment where we found out that there was a vast amount of content missing from privacy policies about the questions. So we found out that the systems where there was predefined content for the questions, it was easier for the systems to answer, but where the content was not available, they hallucinated a lot. Hope that answers the question.
Thank you. Maybe time for one more question.
Thank you for your talk. So I might have missed it, but did you compare to previous work like Polysys or NLP-based tools, and how did the LLMs perform compared to that?
We didn't do it in this study, but all the methods were based on deep learning and natural language processing, and that was different from generative AI based. So for this study, the main aim was to see if these agents are capable of answering the questions. So in future work, we can compare with those studies as well.
Thank you.
So it's more of a feasibility test right now. Maybe we actually do have 1 more minute. Maybe there are more questions to Amir.
So did you have any humans also run your benchmark to see how they would score compared to the Gen AI models?
We didn't compare with any Gen AI model. We just did a study on these models, and it was based on evaluation.
Okay, let's thank the speaker again. For our next presentation, the speaker is Murali Anavaram from University of Southern California. He is a faculty member there. So let's give him a moment to set up. Right, and the topic of the presentation is Edge Private Graph Neural Networks with Singular Value Perturbation. Over to you.
Good morning, folks. My name is Murali Anuvaram. I'm a faculty member at the University of Southern California in Los Angeles. So today I'm presenting the work on behalf of my student who is unable to attend the conference due to visa issues. So here I am. I haven't presented in a conference in a long time, so please pardon me if I forgot how to present it properly. And so with respect to the talk today, we're going to focus on edge private GCNs with singular value perturbation. And so it's funded through NSF, DARPA, VMware, and we have a USC Meta Center that's also funding this work. And so with respect to the outline, I'm going to present some motivation of our work, some background, followed by the Eclipse technology that we developed, and then the experimental setup and results will be presented at the end. So graphs are everywhere. They're from social networks to financial transactions that exchanged between institutions, as well as molecular structures and used in sort of new drug discoveries and so on. And so graphs are present everywhere. And so the issue is you want to learn from these graph structures such that you can figure out what sort of information is hidden in these very large structured graphs. And so one way to learn from these graphs is using graph convolutional neural networks. And what is graph convolutional neural networks? Graph convolutional neural networks basically take two inputs. One is the set of features associated with each node in the graph. And the second one is the structure of the graph itself. So for example, the adjacency matrix that shows what are the nodes connections. And the output, for example, is a node classification. It basically says that this node is a particular type of a node. And so to kind of give you a brief pictorial introduction, so here is a graph. And you can connect that, you can collect the adjacency matrix by connecting the graph, by extracting the edges from the graph. And then you have a features associated with the nodes. So, you know, certain elements that you already know about each of these nodes. And you feed these two things into some sort of a GCN layer, which basically performs certain computations, which takes the matrix A and also the feature X, and computes with and uses a learned parameters W and produces an output called the hidden features. And then you can continue to do this multiple layers, and eventually you will get the node classification output from the system. And so you can kind of train these systems so that the W is learned over time. And so this is a pretty standard process. Many graph convolutional neural networks exist in literature today. And so the question is, these are very popular. So what exactly is the problem with these graph structures and using these in the GCNs? So the issue is that the GCNs are using graph structure, and graph structure is sensitive information. So for example, I don't necessarily want to know who all I'm talking to or who I'm connected to on my social networks. And so same with many of us who are worried about our privacy, and these structures expose a substantial information about who we are in the society. And so let's take a look at what can a adversary do in a system. So for imagine that you have a matrix A, which is the adjacency information, and you said, I'm not going to provide this matrix A to an adversary, but they have access to the GCN that is trained. So this is a pre-trained model. You provide the GCN to the user, and they can essentially query the system many times. So they basically can ask this many questions to this GCN multiple times. And so if an attacker can access essentially the node features and the output of this GCN, they are able to actually go back and reverse extract the adjacency matrix. And there have been studies that demonstrated that one can extract the matrix, adjacency matrix A, using basically called a black box attacks, where you don't even know anything about the matrix A, but you can actually just probe the GCN enough times to extract this information. And this is a problem. So how do we protect the adjacency matrix A? So one way to protect this adjacency matrix A is to actually not have adjacency matrix A inside your training system itself. And so now you want to protect A by not disclosing this A to the system. And how would you do that? Differential privacy. So if you attended session 3B yesterday, there were a whole bunch of talks on differential privacy. If I was giving the talk there, I could avoid the next 5 slides, but for the benefit of those who haven't attended session 3B, I will give you a brief overview of what differential privacy looks like. So what is differential privacy? So here is a adjacency matrix A with a particular graph, features given to a GCN, and it produces basically the node classification distribution information. And then what differential privacy does is it basically adds or subtracts one edge from this matrix. So basically take this adjacency matrix and we essentially flip one bit, 0 to 1 or 1 to 0. And then you get a new matrix. And then in this particular case, we basically deleted this particular edge. And then we feed the same thing back to the same GCN network. And then you compare the output probability distributions on both. And the difference is bounded by basically an epsilon with a probability of 1 minus delta. So this is what we call epsilon delta differential privacy. So this is basically very well-known strategy, particularly for this crowd. And so this is what differential privacy does. And so in the context of adjacency matrices, we're essentially perturbing one weight in order, or one edge in order to essentially protect yourself from disclosing the adjacency matrix entirely to your training platforms. So how do you perturb this matrix A to produce this adjacency matrix A prime? One approach is to essentially take your epsilon and delta parameters for your DP. You have your adjacency matrix. You generate a differentially private noise that is based on these two values. You add that to your adjacency matrix, and you generate a noisy adjacency matrix. And now you feed this noisy adjacency matrix to your GCN and then generate the output from that noisy adjacency matrix. But realize that this noisy adjacency matrix is very difficult to actually get because we don't really have a large variability here, right? You either have a 0 or a 1, connected or not connected. So essentially, anytime you're flipping them, you're essentially either deleting an edge or adding an edge. And so it's not like you're changing 3.5 to 3.4. It's a binary decision process in the case of GCNs. And so this is the fundamental problem. And in fact, this is exactly the approach that is actually taken by DPGCN, one of the well-known papers on differentially private graph convolutional networks. And there are also other approaches such as LPGNet. You can see the paper for more details for this approach. And so the question, therefore, is what are the problems with these existing approaches? So if you look at these measured values in terms of their accuracy on the y-axis with respect to the epsilon, which is the differentially private values that we are interested in, the smaller the epsilon, the better the privacy. But the accuracy of the models such as DPGCN as well as LPGNet is substantially lower than these two blue and the green bars. This blue is essentially saying that, well, I'm just going to use MLPs. In other words, I don't even use adjacency matrix. And then the green bar on the top is showing you the actual GCN with no perturbation to the adjacency matrix. So clearly, you want to do at least as better as the blue, but as the epsilon values go to really small values like 1, 2, and 3, and 4, you're essentially lowering the overall accuracy of the model, in which case, why even bother using the adjacency matrix in these systems, and instead just drop that, right? So that's the goal. So obviously, we're not happy with that. So we want to try to get to a value of a small epsilon and still provide you a substantial adjacent accuracy improvements over this blue bar. And that's the goal of what we want to do. So to sort of summarize, DPGCN, basically A prime shares limited similarity with adjacency matrix A because when you perturb the matrix, you're essentially transforming zeros and ones to zeros, and that's a substantial destruction. Yeah. I can't hear. I'm here. I have to speak into this. Oh. Oh, okay. I thought I was loud enough, but I'm apparently not loud. And so in the case of LPGNet, basically, they don't use adjacency matrix at all. They use sort of a clustered graphs. Again, you see the details in the paper. So what are we interested in? We want to minimally perturb matrix A while producing the differentially private guarantees in the system. And so how are we going to do that? how we're going to minimally perturb matrix A. Here is one approach, and there may be other approaches, but I'm going to present the approach that we used in this paper. So we take the adjacency matrix A, and we are going to decompose the adjacency matrix A using a SVD decomposition. And so you have the basis vectors such as U and V, and the singular value S. So this is what we have. We can take from this, basically the matrix A, transformation of the matrix A into U, V, and a diagonal matrix X, diagonal matrix S. And so now we're going to essentially take this approach, and then we are going to say that let's try to take advantage of this and figure out a way to actually reduce the amount of perturbation we're going to cause in your adjacency matrix. And so how will we do that? And so we're going to observe basically two important observations from this matrix. So we can do this for adjacency matrix A as well as for any adjacency matrix A prime. So basically you perturb one element and then do this all over again and see what happens to the matrices U and V in this system. So this data is showing you, the observation one, is that A and A primes share the principal bases in a large real world graphs. And this is across a whole collection of graphs across many thousands of Monte Carlo simulations. You can see that U and V matrices that are produced from A and A prime, basically if you delete one edge from these very large graphs, the principal basis stays the same. So U and V basically stay the same in these two settings. That's observation one. So keep this in mind. We're going to exploit that property. Observation two. These matrices exhibit a highly low rank structure. And now this is no longer a new news because multiple papers have actually showed that, for example, if you're familiar with LoRa, which is a machine learning system where you actually exploit this low rank optimization. And so this is basically showing you for a variety of graphs such as sightseer and so on, there's a substantially low rank in these matrices itself. And so we're going to take advantage of these two and create Eclipse in basically 3 steps. And so what are the 3 steps? So we're essentially step one, we're going to basically extract the principal basis of A, which is what is shown before as before. And then second is we extract the singular values and we're going to perturb just the singular values because remember that U and V are shared between A and A prime. And therefore I'm going to take the singular values and just perturb only the singular values of this matrix itself. And so what does that mean? I basically generate a random noise. And instead of applying to the entire adjacency matrix, I'm only going to apply that to just the singular values in itself. And therefore, because I'm applying it across only to the singular values, I have the ability to control the amount of noise that goes into the systems. And therefore, I can substantially reduce the amount of noise that is added to the adjacency matrices by themselves. And so now we're going to take this noise addition to just the diagonal matrix. We generate a new diagonal matrix S prime. And since U and V is shared by both A and A prime, we are going to apply this S prime to my adjacency matrix A prime and create basically A prime by using S prime U and V. And so essentially that's the step 2 process. Step 3, remember the second observation? The second observation is that there's a substantial amount of low rank properties in the system. And therefore, we are going to essentially eliminate the ranks that are more than certain threshold. So for example, you set a value to be, I'm going to keep the first 10 low ranks or first 20 ranks, and then essentially substantially reduce the perturbation in the systems. And so when we do this approach, we essentially generate basically a new A prime, which is a prime on a low rank properties. And now we are going to use this A prime low rank as an input to our entire system. So now we are going to take the adjacency matrix that has been perturbed, but in a much more controlled manner, and we feed that to my graph convolutional neural networks. And so that's what we're going to do. And so now we do this, essentially A prime is all that an adversary can know because we never disclosed the matrix A to anybody else entirely in the system. It was never in the system. And so no matter what an adversary can do to the system, they can't actually extract the original matrix A in itself. And this A prime still satisfies the property of the epsilon delta guarantees that we mentioned for the differential privacy, provided the principal bases are in fact shared. And so that's an assumption that we made based on the empirical observations that we showed in the paper before. And so with that, the experimental setup is pretty standard. We use 6 different data sets, both for transductive and inductive settings. For those of you who are not familiar, inductive setting is much harder because you have never seen the graph, but you're going to try to predict from these unseen graphs. Transductive setting is where you have actually seen the graph properties before, and you're going to use that to query the system. We use different model architectures such as DPGC and LPGNet, and then we're comparing it with Eclipse in the system. And so what we can see is that the privacy utility trade-offs, Eclipse achieves better model utility over any of the existing prior works. And as you can see that as we, unfortunately my student changed the color, but this should have been blue, but this is the same blue as we showed before. But as you can see that the Eclipse is better than just using an MLP-based mechanisms, and it actually is much better than any of the existing prior schemes that are shown in the. Of course, there are more results in the paper, including various attack models and so on. So conclusions: privacy is an increasingly precious commodity. Eclipse is a privacy-preserving GCN. It uses SVD and low-rank decomposition, and it works well across a whole range of data sets. And of course, I would be remiss if I don't show my students and my collaborator who worked on this paper. That's the first author, Ting, and then Yunye, and then my colleagues, Salman Awasmer at USC. With that, I'm going to stop and take any questions you may have.
Thank you very much, Murali. Are there questions about the talk?
Hi there, super cool looking result. I just want to make sure I'm clear about one thing. So this doesn't truly satisfy differential privacy because it relies on this, you said on real world data sets, maybe it has a stability property, but you really need worst case. Is that right?
So the assumption is certainly true that you have to have the basis of A and A prime must be the same. Otherwise, you can't reconstruct A prime and still hold the properties. So that's correct.
Okay, yeah. Have you considered using techniques like, say, smooth sensitivity or anything that would maybe like deal with the fact that most data sets are nice to make it bona fide differentially private?
So that's outside of the scope of what we have done. So I don't want to claim something that we don't know enough about. But I can certainly say that there may be other mechanisms to, as you said, some sort of smoothing of the large graphs to make this property hold true, even when it is not necessarily true in some particular graphs.
Cool. Yeah, thanks.
Thank you for your talk. I apologize up front if my question is going to be stupid. Perhaps I misunderstood here something. A prime is a neighboring matrix to A. Namely, they differ in only one entry. And differential privacy, the purpose in differential privacy is to add noise so that for any A prime, not a particular one, for any A prime, you cannot distinguish significantly between the two. And I got the feeling that in your process, you have a specific A prime. Maybe here I missed something. Okay.
Good question. So basically, this idea of adding noise to the to the system by using essentially, let me show. So this approach. So where we are adding a differentially private noise, this is trying to simulate that particular process that A prime that is, remember, in order to actually generate A prime, I only have to flip 1, 0 to 1. That's all I need to do, or 1 to 0. That's all we need to do. But you have to do this like millions of times to actually get the right Monte Carlo-like simulation of different kinds of A primes. So what DP, differential privacy, does is it gives you a very simple tool where you can add a Gaussian noise to the matrix A and create that intuition of what you have to do with a million Monte Carlo simulations without actually doing the simulations themselves. And so this is basically one way to apply differential privacy without having you to do all these various sort of, flip one, retry approach. And so essentially what this is doing is, this is exactly differential privacy as we would imagine, except the implementation is actually adding a Gaussian noise to the matrix A in itself.
Okay, so this is a Laplacian noise, yes?
Yeah, so this is the this is the noise that is adding to this adjacency matrix to generate the differentially private A prime in this case.
And then you round up for the closest 0, 1.
Yeah, so once you add the noise, this is the problem I was mentioning, is that because it's a binary decision process, and typically when you do differential privacy, if you have 13.5 and you perturbing it a little bit, you'll get 13.2 or 13.5 or 13.7. Whereas here, 0 goes to 1 or 1 goes to 0. There's no in between. And that's the problem, is that when you perturb these matrices, you're not pushing them slightly back and forth. You're shifting them to zeros or ones all the way. And that causes a substantial perturbation to the matrices.
Thank you.
Just time for one more question, unfortunately.
I had a question. If the security guarantees between DPGCN are the same as Eclipse, like GCN, you're adding your DP noise to the A matrix, versus in Eclipse, you're adding it to the SVD. And so, is your approach DP with respect to the SVD, or like how do you compare across the two?
Excellent question. In fact, so there are two things why our approach, even though it seems to be adding less noise, still gives you the same sort of guarantees. So I think that's the foundation of the question that you're actually asking.
Yeah.
So there's one critical reason, which is that when you're adding DP noise to the original matrix, as I explained to the previous gentleman, I'm either pushing the values to 0 or 1. And here, when I'm actually applying DPGC and differential private noise to the singular values are not zeros and ones. They're actually real numbers. And therefore, my range of values in our particular simulations is somewhere in the range of 0 to 14. And therefore, we're actually adding noises to the values that are real numbers. And so you're not pushing the zeros and ones all the way, you're actually pushing them slightly back and forth. And that allows us to get the singular value perturbations to be somewhat limited in range. And that is the fundamental reason why we are not perturbing zeros and ones.
Are you clipping the singular values? Like, do you have to bound the sensitivity of the SVD?
Yeah, so the sensitivity of the SVD is clipped to 2, square root of 2.
Okay.
And there is an actual mathematical proof shown in the paper that shows why that's actually the best way to do this.
Thank you.
I invite everyone to find Morale afterwards at lunch for further questions. And thank you once again for the presentation. So the good news is we found the third speaker, but the speaker will be presenting with a recorded talk after all. So we will now get started. So this is Shualing Wen from Stevens Institute of Technology, and the work is titled GCL Link Membership Inference Attacks Against Graph Contrastive Learning.
I'm Shualing Wang, a PhD student from Stevens Institute of Technology in New Jersey, US. Today, I'm going to present our work titled GCL Link Membership Inference Attacks Against Graph Contrastive Learning. This is a joint work with my advisor, Wang from Stevens, and this work is funded by National Science Foundation. Graph neural networks are vulnerable to various types of privacy attacks, such as membership inference attacks, attribute inference attack, property inference attack, structure reconstruction, and so on. Because there are a bunch of words for some privacy attacks against GNNs, so I only cite some typical words here. GCL M2 learn graph representations, namely the embeddings that invite to the augmentations. In this figure, given input graph, GCL first generates multi-augmentation views of the input graph through graph augmentation, such as adding or deleting some edges or nodes from the origin graph, no feature mask shuffling. Then GCL trains an encoder such as GNNs on two of the augmentations to generate a node embeddings by importing a contrast element section, with which the outputs of the node embedding are then fed to the pretext decoder, such as MLP, which depends on the pretext text. The whole model is trained with the machine information-based contrastive laws, such as generation damages. The advantage of GCL model comparing with the supervised or semi-supervised model is that they are independent from downstream learning tasks, and thus they don't require the label data. Label data may be expensive, difficult to obtain, or potentially biased. Your work will focus on the membership inference attack, namely the abbreviated as LMIA, which aim to improve whether any two nodes are connected in the training graph of the given GCL model. None of these pre-work have studied the privacy vulnerability of GCL models. And we consider following two research questions in our work. Are GCL models vulnerable to LMIA? And how do we define against LMIA and protect the privacy of GCL model? When we adapt the existing LMIA to the GCL model, which is similarity between the embeddings and the feature, we found the challenge caused by dynamic link membership in the views, because the membership of any node pair changes across different views. For example, in the augmentation of edge removal, the member edges in the chain graph may become a non-member edge in the augmentation view. And when edge addition, use the non-member edge in the training graph and become a member edge in the augmentation view. In this work, we make foreign contributions. We designed GCL leak, the first LMIA against the GCL model. We demonstrated the effectiveness of GCL leak against the GCL model. We devised two defense mechanisms to mitigate the vulnerability of GCL models against GCL leak. And we demonstrated that both defense measures significantly reduce attack accuracy while preserving accuracy of GCL model through empirical evaluation. Next, I'll introduce the paper for the four aspects: the design of the attack, the evaluation, defense mechanism, and the conclusion. We consider the adversary situated in the federated setting, potentially an honest but curious server. The adversary leverages known embeddings within all materials obtained through white box access to the type model or LMIA inference. Given a graph G, we assume that the adversary has a point knowledge, non-embedding of the type graph from each application and the shadow graph, which may have its own data distribution, attributes, and may from different domains of a type graph. Then the LMIA is designed as a function, given a set of non-embedding of the type pair of JVK from each application, and the adversary knowledge. The adversary can make the JVK to the binary value then whether no pair VJVK is a member or not member in type graph. The figure shows why when we adapt the LMIA to the GCL model, which is similarity between the embeddings as a feature, the dynamic linkage in the views inference attack performance. The figure shows the cosine similarity distribution for both members and non-members. From figure A, in which we use the link status in each application as a membership label, we can see members and non-members in our application views can't be distinguished based on their embedded similarity. This is because the non-embedding and the similarity is expected to remain unchanged or slightly change despite the membership variation of application views. From figure B, in which we use the ground truth label as a membership label, we observe that the ground truth member and non-member are partially overlapped. And from figure C, we observe that the ground truth member and non-member are well distinguishable by the embedded similarity of those whose members are the same as the ground truth members. In summary, augmented member and non-member edges are not distinguishable by embedded similarity in augmented views. And the ground truth member and non-members are well distinguishable by the embedded similarity of those whose augmented membership is the same as the ground truth membership. Based on this observation, a naive method to estimate attack features from embedded similarity of those node pairs which have consistent augmented and ground truth memberships. However, there is a question that how to deal with the identical membership information that is only available for the attack chaining phase but not for the inference phase. So next I will introduce our type model, how it can solve the problem. In attack chaining, the generation attack as the model embedding run all the kinds and generates attack features based on their embeddings. In attack monitoring phase, the attacker changes the attack classifier with the matching data. And in the membership phase, given the embeddings of the pair of nodes, the attacker generates the attack feature, which is then input to the chain classifier to predict the link membership states of the node. And to adjust the challenge covered by the dynamic membership in different augmentation views, we design our attack classifier and the learning using privileged information paradigm, abbreviated as RUPI. RUPI leverages the privileged information that is available during the training but not during testing. In our context, the privileged information refers to the same membership information. We use a rule-based method. First, we call attack chain data generation together with the attack monitoring phase on server side as attack chaining. The solution one is that we use an identical membership-based method in a chain set for both members and non-members. Only similarity from augmentation with identical membership is used, and the same number of embeddings from all augmentations are randomly selected. And P plus and P minus represent the identical membership augmentations from members and non-members. Solution 2 is that we regard the membership change in the chain set as a secondary target, and the learning model's objective is to minimize the loss associated with both the primary target and secondary target. It can be regarded as a multitask learning task. Y represents the ground truth membership, namely the primary target, and the Y star or Y2 dash represents the membership in augmentations, namely the secondary target. The third solution is that we regard the membership change in the chain set as a secondary feature. The learning model trains a secondary classifier with secondary feature, which includes the membership status in each augmentation, and whose output introduces a regularizer term to the load function of the primary classifier. Here, X represents the similarity features, which are the combination of similarity of each augmentation, and S2 represents the combination of similarity of each augmentation together with the combination of the membership in augmentations. Next, I will introduce the evaluation part. We can consider three real-world sets, namely Chorus, IC, and Facebook dataset that are popularly used in the graphical engineering. We consider more popular GCL models, namely GRACE, MVGIL, GCA, and CCSFG. We use attack accuracy, AUC, true positive rate, and false positive rates to measure the attack effectiveness, and use AUC of some node classification to measure the attack model performance. We compare with attack model with four designs. Design A is existing embedding based on MIA, which utilizes the embedding from final embedding, not for augmentations. And baseline B is the model without looping, namely directly calculating the similarity value of the pairs in all augmented views. And baseline C is the combination of embeddings, which replace the combination of embedding similarity with the combination of embeddings. And baseline D is threshold-based method, which is an example of three threshold-based sub-attack, and each attack is based on one of the similarity metric. The figure shows the effectiveness of MIA against the GCL model. We observe that the attack accuracy of the attack is significantly higher than 0.5, and our attack output baseline in all settings. The figure shows the impact of various loop methods. We observe that our solution outperforms either two methods across all settings, in which we use an identical membership-based method in a chain set for both membership and non-membership, and the members only. The similarity from augmentations with identical membership is used, and the same members of embeddings from all our augmentations are randomly selected. Let's start introduce our defense mechanism. The key idea of our defense mechanism is to add noise to the node embeddings from target model. So we have the following to defense: the full noise, which injects the Laplace noise to all dimensions of the node embeddings, and the partial noise, which is selected as noise only to the least important dimensions of embeddings, which includes three steps. First, we estimate the importance of embedding dimensions by using sharp value-based method. And second, we rank the embedding dimension based on the importance. And third, we add Laplace noise to partial embedding dimensions of the lowest importance. And D is the embedding dimension, and R is the perturbation ratio. This figure shows the trade-off of our defense mechanism compared with the baseline against MIA on GCL. We vary the node scale and perturbation ratios and evaluate the attack accuracy and target model accuracy under different settings. Then we process the trade-off curve. Each point corresponds to a correct pair of the attack accuracy and target model accuracy. We compare our method with a differential privacy-based method, which acknowledge the gradient of each iteration, and dropout-based method, which should drop out each layer and each iteration. One figure, we observe that the p-noise outcomes on three methods concerning the trade-off between the attack performance and model quality. When attack accuracy approaches 0.5, the target model performance of our method is higher than the baselines. To summarize in the work, we designed GCL Lake, the first white-box link inference attack against GCL models, and we propose effective defense mechanisms that introduce protection to the least important information of values. In future work, we will investigate the vulnerability of GCL models to other types of attacks, such as the attribute inference attack and model inversion attacks. We will design alternative effective defense mechanisms against GCL leak. Okay, this is the end of my talks. Thank you for your attention. I'm happy to take questions.
Let's thank Xiaoling for this impressive work.
Yeah, hi.
Xiaoling, can you
hear
us?
Yeah. Yes.
Oh, hello. We have time, unfortunately, to just one very brief question. I will quickly check if there is any in the audience. So a question from me would be, you acknowledge by the end of the talk that this is a white box attack and this is the first of its kind against GCL. So you require access to node embeddings of the target graph. And I was wondering if you believe there are real world settings where this could be used this way. And if so, what would it take to launch such an attack? And if not, how would you continue exploring security and privacy of GCL in more realistic setup?
Yeah, thank you for your question. Actually, our attack is based on federated learning, and we found that in some federated-based scenarios, the clients will upload their embeddings to a server at each iteration. So the server can get the embeddings of the GCL model in each iteration, and we assume the server is curious, honest but curious. So this is our setting. The server is attacker. Yeah, so we think it is realistic. Yeah.
Yes, thank you so much. Yeah, thank you for clarifying. Okay, let's thank Xiaoling again.
Thank you.
Next up, we have John Abascal. John is a PhD candidate at Northeastern University. And this research is titled TMI, Fine-Tuned Models Leak Private Information from their Pre-Training Data from their pre-train.
All right. Hi, everyone. I'm John, and today I'll be talking about our work on membership inference attacks on fine-tuned machine learning models. And this is based on joint work with my colleague Stanley Wu and our advisors at Northeastern, Alina Oprea and Jonathan Ullman. So consider the typical machine learning setting where we have a data set D that we use to train some machine learning model that we'll call F. And users can make queries to this model by sending their own data and getting some response back, usually in the form of a prediction. But now suppose that this user is actually malicious and wants to extract something about the data set D from the machine learning model F. There's tons of prior work on privacy attacks in machine learning. And in this paper, we specifically study membership inference attacks. These attacks are the most commonly studied privacy attacks on ML, and they represent this very fundamental form of privacy leakage that has direct connections to differential privacy. The general strategy for these attacks in this query access setting is that the adversary would take some point, we'll call it a challenge point, and they'll query the model and use the prediction confidence as a test statistic to make this determination as to whether the challenge point was in the training data set, which we'll denote as in, or not in the training data set, which we will denote as out. So before I talk about our specific attack, I'll give two important pieces of background. The first of which is differential privacy, which is a framework for protecting sensitive data that still allows us to conduct statistical analysis on it. And we'll say that a randomized algorithm M is epsilon differentially private if for any two data sets that differ by at most one individual, this inequality holds. And all that this inequality enforces is that when epsilon is large, it should be easy for an adversary to distinguish whether I use data set X or X prime, like as an input to my algorithm. And when epsilon is small, it should be difficult for an adversary to perform this distinguishing test. And you might notice that this is exactly the same distinguishing test that a membership inference adversary has to perform. Thus, by definition, DP bounds the success of these kinds of adversaries. But how do we practically achieve differential privacy in machine learning? Well, all that we have to do is make a couple small changes to our normal gradient descent algorithm. So first, we clip the gradients so that everybody has like kind of a bounded influence on the final model. And then we add Gaussian noise to blur the direction of their contribution to the model, right? And we repeat this over and over again until convergence. But I should note that since we have to add Gaussian noise, there's necessarily this like fundamental privacy utility trade-off when we want to protect this data using DP. The second piece of background that I'll talk about is transfer learning, which has emerged as this really popular technique as models are becoming increasingly hard to train nowadays. And fine-tuning really allows us to use the power and generality of models that are huge, like GPT-3 or GPT-4, without needing the computational power to train them from scratch or needing that much data for whatever our specific task is. And in this work, we consider two kinds of fine-tuning, namely feature extraction or final layer fine-tuning, where all of the weights except for the final layer are frozen, and then we train the final layer on our downstream task. And full model fine-tuning, where we could take any subset of the parameters and fine-tune them on our downstream task. So now to bring these two pieces of background together, there's been a lot of recent work that's used transfer learning as a solution to this privacy utility trade-off that we face when we're training models with DP. And these works are really aiming to leverage the generic features that are learned from this publicly available data before ever touching sensitive data at all. What they don't address is that these pre-trained models might themselves carry privacy risks and could potentially lead to unintended privacy risks when fine-tuning with DP. So to investigate this, we asked two main research questions. The first two main research questions. The first being, do fine-tuned models leak information about their pre-training data at all? And then the second question is, what implications does this have for fine-tuning with DP? So towards this first question, we slightly redefined the membership inference threat model because now the adversary, there's this kind of intermediary between the adversary and what they want to learn about, which is the pre-training data set. So suppose that the challenger, the model owner, samples some data set, D pre-train, and they use this to train some model that we'll call G. Then the challenger will sample a fine-tuning data set and combine this with the pre-trained model to produce a new model that we'll call F. And this is the model that the adversary will be able to query. Then the challenger will flip a coin. If the coin lands on heads, they'll sample a point from the underlying distribution that was not seen in training. And if the coin lands on tails, they'll sample a point directly from the training set. They'll then send this point to the adversary, and then we as the adversary have to determine if this point was in or out of the data set, right? So to realize this attack, or this threat model, we create a meta-classifier-based membership inference attack that we call transfer membership inference, or TMI. And the attack algorithm is as follows. Suppose that we're given some victim model F and sampling access to both of these training distributions. First, the adversary will train a bunch of shadow models that either do or do not contain the challenge point in order to mimic the behavior of the victim model. Then they'll query the challenge point, or they'll query these local models on the challenge point and build a local data set of prediction vectors. Then they'll train a classifier on this local data set and query the victim model on the challenge point to get another prediction vector. And lastly, they'll compare the victim model's prediction vector against their local data set and make some kind of classification. Right, for our experiments, we look at 3 pre-training tasks and 6 fine-tuning tasks across both vision and language architectures. And as our success metric, we observe the true positive rate of our attack at low fixed false positive rates. So what this tells us is how often our attack correctly identifies membership while making very few false accusations. So in our first experiment, we look at models that have only been fine-tuned in their last layer. This orange ROC curve represents the state-of-the-art attack from prior work, which we use as a baseline. We kind of just transplant it to this new setting. And this red dashed line shows the same attack, but run directly on the pre-trained models. So like without this intermediary. And this is kind of the best that we could hope to do. So you can see that the blue ROC curve, which is the performance of our attack, gets quite close to this upper bound. When the model's parameters are updated, necessarily we lose some information about the pre-training data set. So our attack success slightly decreases, but overall we're still able to achieve high accuracy in this setting. So these experiments kind of answer our first question, but now we want to know what potential implications could this have for fine-tuning with DP. So consider the following thought experiment. Suppose that I'm a customer at a company that claims to use private machine learning, but what they're really doing is taking some pre-trained LLM and then fine-tuning the last layer with very strong privacy parameters. Then I could make the following query to this LLM, and for some reason it outputs all this sensitive information about me. So because this company advertises that they use private training, I have this reasonable expectation that my data should be protected by the guarantee that they advertise. But this obviously isn't the case. So how could this happen? And the reason why this happens is because the public data sets that are used to pre-train these models often are scraped from the web or user data. And these data sets exceed terabytes in size, making them extremely difficult to comb through for duplicate records of sensitive data. And this data can also be published unintentionally and gathered from users without their explicit consent. So if these pre-trained models are trained on this unintentionally uploaded data, we're potentially amplifying the privacy risk of these people. And furthermore, companies use their own proprietary web scrape data sets internally that they use to pre-train their own models, which they offer to customers to fine-tune as a service. So to see if there actually is leakage in this setting, we run the following experiment. We ask, well, what could go wrong if these two data sets overlap? And what we do is we fine-tune on some data that overlaps with the pre-training data set, and then we try to attack the points that are in this overlap. And we find that nobody in this overlap gets the stated privacy guarantee. So this green dashed line shows the upper bound that DP imposes on the true positive rate of a membership inference adversary for epsilon equals 1. And you can see that our attack's true positive rate is much higher than this. And this really just happens because the gradients in pre-training are not clipped, so they have like unbounded sensitivity. So to wrap things up, transfer learning has emerged as this really popular technique that allows us to leverage the power of foundation models for our specific tasks. And fine-tuning with differential privacy kind of gets around this privacy utility trade-off that we run into. But our work finds that fine-tuned models do indeed leak information about their pre-training data sets. And this could lead to unintended leakage when fine-tuning with DP. We have many more results in the paper, so please take a look if you're interested, and I'm happy to take any questions that you may have. Thank you.
Are there questions for this study?
So one of the fundamental assumptions is that the pre-trained models use data that is not supposed to be private, correct?
Yes.
But in your observation, you can extract information from that data set even after it has been fine-tuned. That's what you're claiming. But if you told me that I don't want to recover even that information, maybe I would not have even pre-trained the model using the approaches that I have used. So I'm kind of at this confusion as to you are testing me on an exam where I was not even prepared to do. So that's the foundational problem I have with what you described. So could you sort of explain to me why would I be interested in understanding this particular
Right.
leakage.
So I think the main issue is that we often, I guess, like as model owners, even if you're like a large company, even if you're a model owner, like a large company, there's a chance that you didn't pre-train the model that you're fine-tuning with differential privacy, right? So suppose that you have some sensitive record that appeared in the data breach, it gets scraped, to pre-train this large model. I never knew that that was included in the training set, right? So now if this company goes and uses this sensitive record in their fine-tuning set and says, well, we're going to protect you by, fine-tuning with differential privacy, you have this expectation that your data should be protected. And we're making the argument that it indeed is not protected, right? So the whole point is like, we don't control the pre-training process. So it's basically kind of like a black box. You don't know what's going to happen.
There's one more question in the back.
Thanks for your presentation and also very insightful analysis. So I'm wondering, so you just mentioned that since the pre-training process is not protected by DP, so the sensitivity might not be bounded. But have you ever tried, for example, pre-training a larger data set? I would imagine that, for example, if your pre-training data set is larger, then the sensitivity or contribution of single data record would be smaller. And,
Right. I think it might be the case that models are just too large now and can memorize way too much data. So this might still be a problem no matter how large the data set is. Right.
Maybe just one more follow-up comment. So I sort of agree. I think this is open, but I'm just wondering, for example, if we pre-train a data set like say 1 billion tokens, and is it still that? I mean, I'm curious about the potential privacy leakage. Is it still that severe? Because I would imagine the sensitivity would be very small.
Yeah, I mean, I don't know. I can't really answer that. Okay. But I think for at least very large models, yeah, you would still expect that there's some leakage.
Okay, thank you.
Thank you for the interesting talk. You may not be able to answer this question because I guess it's more general, but I was wondering if you observed in the real world any of these issues in some of the models like GPT-4 or anything where there was some data that was supposed to be private, like some PII, and then that was able to be extracted.
Right. So there was one instance that kind of made a headline where Copilot, which I believe is like based on GPT-3 or GPT-4, but then fine-tuned on GitHub code, leaks someone's crypto wallet key. So this is like a serious problem that could actually,
Probably a general summarizing question. So do we interpret your study as some kind of awareness study about the problem that theoretically we do know, but it is overlooked? Or do you also suggest some solutions on how to approach this practically?
Right. I think that this is more of just like a study of what can happen. As for solutions, it's still pretty, like, it's an open question, like how should we approach this? Because we already have pre-trained models that are out there that have sensitive information in their pre-training data sets. But I guess my opinion is that maybe the data curation process has to be a bit more rigorous.
And maybe we could do some kind of membership analysis of our own confidential data against the pre-trained model.
Yes.
Okay, thank you very much. Let's thank John again. Next up, we have Adia Kavia from University of Haifa. She's a faculty member there. And the topic is privacy preserving feature selection for sparse linear regression.
Okay, I'm going to talk about joint work again, and hi, who are in the audience as well.
I'm sorry to interrupt you so early.
Here, because we have good attendance and they will hear you reminding me. So the scenario consider is we have multiple data owners, the hospitals in the picture, and they want to do some computation on their private data, and they use a server, a third-party entity, which is depicted by the cloud here, to give them these machine learning services. but they don't want their data to be revealed, not to the server, not to any other of these hospitals. So they want the process to be computed securely, say with MPC or FHE or other techniques that we have. If you want to guarantee protection, you really need to protect the entire pipeline. It's not enough just to protect, say, the model evaluation or the training in the end if the server is exposed to data in preliminary stages of learning, like the feature extraction or data protection. And our focus in this work is on the feature extraction phase, which is the phase where you decide what are the predictor or the variables that you're actually going to give as input to the training algorithm. So if we look at the feature selection, there are many methods. It's like machine learning is like this huge tool set. None of these methods is like the winner. We need the entire tool set because different data domains and applications need different tools. And we can categorize the techniques to 3 main categories: the filter methods, embedded methods, and wrapper methods. For the former 2 categories, there have been already privacy-preserving solutions. For the latter one, this is the focus of our work. We give the first privacy-preserving feature selection in the wrapper method. So just to give you a glimpse of the cons and pros of each method, a filter method gives a score to each feature in isolation, say by the correlation to the target values, and then it discards all the ones that have low scores. And this is great because it's very fast, but it completely ignores all the dependencies between the features. So possibly a feature on its own is a very weak predictor, but if you combine it with many other weak predictors together, they give a much stronger prediction. Embedded methods are things like decision trees or lasso regression. The training algorithm itself actually selects the features. When you train a decision tree, each node has the feature that you have to look at. So that's also, you don't need to do a separate feature selection. It's part of the training, which is great because it's inherent. But you can't always control the selection process as you wish. For example, in some settings, it's really important to have very few features. Suppose, for example, that you want to use the your model for medical intervention, where just reading the feature requires some intervention or some medical device is expensive, then you really want to limit the number of features. You want the model to be sparse, to have few features. And with intrinsic, this embedded method, it's harder to control the number of features that you have. And the last method is the wrapper method. This says that you know the model that you want to train, say a regression model, do this iterative process. Train the model on the features, rank the features by their weight in the model, and just drop off, discard all the ones that are not as important. And then redo it on the surviving features again, until you remain with just the number of features that you want. And this is one approach is also a top-down approach that you gradually add the features. And in some data domains, for example, in gene expression data, this is actually the method of the leading methods for feature extraction. And a key advantage is you can really fine-tune the sparsity of the model as you wish. Just continue dropping off until you reach the exact number of features that you want. The downside, it's very slow. You do repeated training, multiple training rounds, and this is a slow process. But we don't always care if you're later going to use these medical devices for many predictions, then adding a few more hours to the training process or even a few more days, it really of little significance. So this is what we do. We give a privacy-preserving solution in the wrapper method, which you call secure iterated ridge. We train a sparse ridge regression model. And the security that we have is in this 2-server model. So the server is going to be actually 2 non-colluding servers where the data owners are going to just encrypt the data with a key produced by one server and upload it in encrypted form to the other server. And now they can go, the server is going to merge the data using homomorphic encryption. And now the data owners, they can go to rest. The rest of the computation is a 2-party computation between the 2 servers. And this is a new part, how we actually do this feature selection on the servers. Now, the first idea that we have, let's just plug in what we already know. There have been privacy-preserving training solutions for ridge regression model. Let's just plug them in, use the known words to train a model, then rank the features and discard the lowest ranking ones. But when we try to apply this, we see that every step has a problem. First, I say discard the features, but the output of this feature selection is just the final set of features. And even that, we give an alternative to give an encrypted form so that you don't actually want to reveal anything. We can't tell the servers what features we discard in each intermediate steps. This leaks information. And actually, we give in the paper concrete attacks that show that this is really a breach of security even on natural data input items. So we cannot really discard it. What about ranking? Ranking means that I want to compare features, to sort them by size. And for comparison, I really want the data, if I wanted to do comparison over homomorphically encrypted values, I want it to be in binary representation. That's where comparison is fastest. But the training for the existing work gives the model with features embedded in very large rings like pair rings. In integers model where n is 1,000 bits long. So I have a discrepancy between the way data is represented as the output of the training stage and the way you want it to be represented for the ranking part. What about training? Here is maybe the biggest problem. Prior work on privacy-preserving training, they produced the model in clear text, and because they allow to produce it in clear text, they give it in kind of a half-baked form. They give the model in a way that you need to do a very expensive post-processing on the model after it's accumulated. And this post-processing is fine to do on clear text model, but in our setting, we have to have all the intermediate values encrypted. So the model has to be encrypted, and then this post-processing is much too heavy to apply. Okay, so these are the problems that we faced, and what are our solutions? So first, instead of discarding the features in the clear, we're going to do it obliviously. And the way we approach it is that each server is going to sample a random permutation. Server 2 is going to send his permutation matrix in encrypted form to server 1, and the server 1 is going to apply both these permutations, P1, P2, to shuffle the data. So that after this shuffling, none of the servers knows what index in the data to look at means with respect to the original features. So we can just give these indices because they're just random numbers that leak no information of the original indices. What about the ranking? Here we plug in a new component that we designed for an arithmetic to binary mapping. That's which is a method fine-tuned to the parameters that we have. So we get the model from the training, and we change the representation of the data using a short 2PC computation to binary representation. And I think the most interesting part is the training part, where we observe that we don't really need to output the same model as a real regression model in the end. What we want is just to have the same ranking of features. And to have the same features, any model that is scale up at the same scalar for all features would do. And this we show can be done much more efficiently. We can produce a model that requires no post-processing, so we can continue processing it in an encrypted form, and it achieves the same ranking as a real ridge model. So I don't have much time. I'll just give a hint that the scale model, we really rely on some nice algebraic identities that allows us to transition from the standard solution to ridge model, which requires inverting a matrix A, to a solution that just requires computing an adjoint of the matrix, which involves only multiplication and additions, no inversions, no division, and this really simplifies or eliminates the need for what's called rational reconstruction in the post-processing. We evaluated our subsystem that we build on gene expression data, where this method is useful. Gene expression tells you what genes are actually being used in the tissue now, what are expressed to produce the protein. We used real data sets available online and the code is, of course, open source. And we see that for one iteration, if you select 10 out of 40 features, that takes about an hour. If you want to do really fine-grained selection of taking the features almost one by one, we do 15 iterations that takes still under a day. And the performance really scale up very nicely in the number of data owners and the number of records. When we multiply the number of data owners from 10 to 100, so the factor of 10, or the number of records from roughly 800 to roughly 800,000, sorry, many more records, the runtime stayed roughly the same. This is for selecting 2 out of 10 features, roughly 2 hours, regardless of the number of data owners or records. In the number of features, the scaling up is not too good. When we go from 10 features to 40, you see the runtime is from 2 hours to a day. That's a big gap. And then we recommend that if you want to really select from huge number of features, like we started with a gene expression with 10,000 features, you do a hybrid method. You start with filter method to quickly sieve out many of the features and then fine tune on the remaining features with wrapper type methods. So just to summarize, we give the first privacy-preserving feature selection in a wrapper method. We show that it can be used to select a sparse ridge regression model, and we evaluate it to gene expression data. I think the new tool of this scaled ridge is actually of independent interest, and later today I'm going to discuss in a poster session a follow-up work that uses it for epigenetic age assessment with a privacy-preserving method that again has this use of ridge in iteration. There are expectation maximization iterations, and the fact that we don't need post-processing allows to use it as a component in a larger computation. And one last note, the training of the model, we use it for ridge, but you can replace ridge with any other model that you like and just plug in the training step with another method. Our framework and most of our code is still useful even for other methods.
Let's thank Adi for the presentation. We have some time for 1 or 2 very brief questions. Yes, in the middle of the room.
Thank you, Adi. Quick question. You mentioned that in order to protect from the servers the identity of the features that were selected, the data owners choose a random permutation?
It's not the data owners, it's 2 servers.
Yeah.
They obliviously permute the data matrix at the beginning.
Okay.
And then they hide the identity of the intermediate selected, discarded features. The final model, we have a kind of 2 options. One version outputs it in encrypted mode, and then it's hidden all throughout. And the other one says the final model, they just reveal in the clear, but not the intermediate models.
Okay, so it's the servers who select the permutations.
They select it and they select it obliviously. None of them knows the permutation. Each of them selects part of the permutation. The permutation together is the product of P1 times P2. So
Yes.
none of them, each server knows just one of the part of this product.
Okay, thank you.
We're out of time for more questions, but please find Adi later on at lunch and let's thank her again. Now we have Huang Nguyen setting up for the final presentation of the session. We're a little bit over time, but there will be a very long queue at lunch, judging by yesterday. Oh, okay, so the setup is there. Can you try out the clicker? Yeah. So Huang is a PhD candidate at ETH Zurich, and this work is titled Model-Driven Privacy. Over to you.
Thank you so much for the introductions. I hope the people on Zoom land can also hear me. So my name is Huang Nguyen, and I'm a PhD student at ETH Zurich. Today it's my pleasure to be here to present to you our latest work related to the new software methodology that incorporates privacy requirements into the early stage of the system design. It is called, as you can see, Model-Driven Privacy. This work is conducted together with my 2 supervisors, Dr. Sergeant Christie and Professor David Basin. So I would like to begin this talk with a brief motivations of the number of GDPR sum of fines. So as you can see, since the beginning of the enactment, in 2018 of the regulations, the number of files and the sum of files has been, increased rapidly. And GDPR is not the exception because there are other sorts of requirements as well, depending on the country, on organizations, and also on the domains of the system. For example, in healthcare, they have different set of privacy policies. Among of these sources, there are common requirements, namely some of them like data subject consents, purpose limitations, data minimizations, and storage limitations. In this talk, we rely solely on GDPR as our sources, and we focus on the two most common requirements, which are so-called the purpose limitations and data subject consents. So to recall briefly the definitions of these privacy requirements in the GDPR, purpose limitations refer to the Article 5, Section 1B, saying that personal data shall be collected for specified, explicit, and legitimate purposes, and not further processed in a manner that is incompatible with those purposes. While data subject consent refer to the Article 7, Section 1, saying that processing personal data shall be lawful only if the data subject has given consent to the processing of his or her personal data for one or more specific purpose. So these are the definitions in the regulations. And turns out in software development, it's not easy to implement or handling such privacy requirement. In fact, it is a challenging problem. Is it challenging because due to the lack of effective language and tool to specify these privacy requirements? And traditionally, the developer have to, interpret these requirements manually, and then in an ad hoc, when they have to implement this thing in an ad hoc manner, and as a consequence, there is a huge gap between specification and implementations. And also, moreover, whenever the application changes or the privacy requirement evolve, as we can see, that's evolved quite often. The maintaining of these applications can take a lot of effort, while it gives very little guarantee of correctness. So in this work, we try to bridge the gap between specification and implementations by promoting this new development methodology called model-driven development. And in model-driven development, the developer will define models. So these models are not AI models. These are also mathematically defined objects, but they specify different aspects of the system. And we rely on model transformation to take this model as an input and generate some executable code of the target system. As far as security is concerned, so there's the work of Lodderstedt and Order in the 2010s, I think, that showcase this approach in security. So they define security model which comprise of different access control policy, and they have relied on the model transformation that they wrote to generate access control assertions. In our work, we also do that, but we extend further, and we define a privacy policy. In this case, is related to the purpose limitation and data subject consent requirements. We extend the model transformations, and we generate privacy-related artifacts. So in our approach, we're using a formal language with precise definitions and semantics to specify privacy requirements. We rely on code generation to generate privacy artifacts that are cross-cutting and correct by design. And whenever something changed, let's say if the privacy requirement changed, we only need to change the privacy requirements and we regenerate the code. If the application changed, we change the data model and so on. So there's like separation of concern right there. So our main contribution is a threefold. So firstly, we define the new modeling language to specify privacy policy. Then we extend the model transformations that generate privacy-related artifacts, and we implement tool mapping that targets C# and Python programming languages. And finally, using this prototype, we were able to also implement several case study applications on different domains and use them to evaluate the effectiveness and development effort of our approach. So I just would like to quickly introduce the methodology in detail. So this is the figure. On the left-hand side, you can see the input models. The right-hand side is the output artifacts, and in between there are arrows that represent different kind of transformations. So let's start quickly with the input models. In our approach, we have two input models. We have a data model and a privacy model. Data model is basically express the classes of the system. So for example, take the conference management system as an example, then the data model may contain classes like researcher and paper class, and then they have attributes and appropriate association and methods. For example, in researcher, you can see a researcher can have a name, can have a student status, and it has a recommend paper method that returns a list of recommended paper to the researcher, for example. Now, onto the privacy model, one needs to define a privacy model in several steps. So first, they have to identify which class is the personal data. In this example, let us assume researcher is personal data. Then we also have to define purposes. For the sake of simplicity, in this example on the slide, we only have the application as one example, one purpose, which is to recommend paper to the researcher. Then one also the next step is to define declared purposes. So you can think of these declared purposes are like purpose-based access control policies, which comprise of 4 components: the purpose per se, the actions, then the resource that the action acted upon on, and an additional authorization constraint. In this work, the constraint are expressed using first-order logic specification language called object constraint. And finally, we need to link the method in the classes with the actual purpose. In this example, we link the recommend paper method in the researcher class with the actual purpose of recommending paper to the researcher. Okay. Then with these two models, using model-to-model transformation, we extend further the data model with privacy notions. For example, we know that in the privacy model, we say the personal data is the researcher. In the extended data model, we extend the researcher class with appropriate personal data class. Then in our work, personal data also assumed to have an owner, and this owner has the ability to grant or revoke consent on different kind of purposes of this data. So this specification, as you can see, is already displayed in this extension of the data model. Finally, in the output artifact, due to time limitation, I don't think I can go through all of it. So I will just list out of the artifact here. So we generate different artifacts like class implemented stuff, policy notice, enforcement mechanism of different types, consent mechanism, consent collections, and also purpose tracking. Here are some key designs. So for the classes and method stuff generations, the methods are generated with an empty stuff that leave for the developer to implement their own business tasks. And they will also be annotated with the actual purpose. So you can see in the snippet, the first line is actually the label for the actual purpose. Then also the privacy notice is also automatically generated, and then the underlying mechanism is the consent collections. We implement 2 prototypes for this transformation. So we implement prototype targeting C# and Python web framework. And using these prototype, we were able to implement different case studies ranging from different range of domains. So on the left, the mini tweet is the social networking side, the conference management system example that I show you, and on the right most is the health record manager. Now onto the research question, we would like to, in this talk, we would like to represent 2 answers to the 2 research questions that we have in the paper. There were more. I encourage you to read the paper if you want. So we would like to answer the question of development effort and performance overhead. For the first question, we set up the example such that in the context of the conference management system, the developer have to first define the model, then rely on the generated of the code, and then fill in the empty stuff to complete the applications. And here's are the numbers. So for the first step, for defining the model, one would need to define 13 lines of code for the data model and 20 lines for the rest of the models, which means the security and privacy. The generated code these are the result of the generated code, and then the implementation that the developer required to fill in is this number of line of code. And in summary, when we sum up everything, we notice that the developer only need to implement manually around 50 to 60% line of code in the overall code base. The rest, 84% line of code is generated automatically and is correct by design. Up to the question of the performance overhead, what we did is we find a mini tweet, which is the social networking site on GitHub, which is insecure, so there's no privacy checks anywhere. So we call this a baseline applications. Then we take this and we refine further by implementing manually the privacy checks for this application. We call it secure applications. And in parallel, we implement this application using our approach. So we call it flash applications. And we execute, there's an endpoint in the application called public timeline that show the public timeline of the user. and we run the experiment on this endpoint and with the pagination of 30 messages, and we see that although the performance overhead is noticeable, but after the 30 messages, it seems to be modest compared to the manual implementation and is acceptable. For further work, we would like to extend it in different dimensions. First, we want to extend with all the classes requirements, like data minimizations or storage limitations. We would also want to prove formally the correctness of the transformations. And we would also want to conduct an empirical study on larger scale of user. So with this, I could conclude my presentations. Thank you so much for listening, and I would love to take the question now or during the poster. Thank you.
Thank you, Hoang. Are there questions about the work?
Thank you for the interesting talk. Perhaps I missed something. So when you generate the code, I saw that you have the code annotations. And for instance, let's say that you have a specific purpose that comes from the privacy policy, but then you allow the developer to kind of put whatever code you want inside that stub that you automatically generated. So what is there to enforce that your, let's say, code label that you put, it's for some specific purpose, but then the developer can use for whatever other purpose. And so the code that you generated actually is not connected to the implementation of the development.
Thank you for the question. I can answer this question by explaining the process that we have in mind for the software development process. So in this process, we imagine there are different actors in this software system. So you have an engineer who just basically care about the business process. There will be a security engineer who just care about security aspect, and also similarly, there will be a privacy engineer that care about privacy. So privacy engineer, the task of this guy is to implement privacy model. He has to think of which process and which purpose corresponding to this process, and this guy will just create the privacy model. Then the one who have to implement the business have to make sure that they have to implement in such a way that it doesn't use more information than it needed. So that's why you see the method stuff right there. It is there for the developer to really implement the business logic. So it's actually kind of responsible of the developer to implement it in a correct way, correct here with respect to the privacy policy. So if use more information that is needed, then the application won't work.
Okay, thank you.
Thank you.
Thank you. I had a question regarding if you would make changes to policies because you generate codes, and I'm wondering what would be the impact if you make some modification to a policy. Would that require substantial refactoring effort or re-implementing, or can you deal with some changes to these policies?
Yes. So in the model transformation, we design the transformations in a way that the generated artifacts are cross-cutting. Cross-cutting here means that it will be separately from different parts. So for example, if you change the privacy requirements, the generated artifact won't affect the code that the developer implemented.
But it will have impact if you make changes to purposes, for example, because you have these generated stubs that do.
It will not be significant, and the effort that require you to change the application, like for example, change the purpose, will not be major. It will be something.
Okay, thank you.
Let's thank Hoang for the final presentation of the session. Many thanks to you all for attending the session and asking nice questions. And now we are moving on for the lunch break.
Is this working? Okay. Yeah, so welcome to the session on human privacy. And just to start with a couple of announcements. So somebody lost some earbuds. So if you're missing some earbuds, go to the PETS registration desk. And then also, if you see people standing on the outside and you're sitting in the aisle, if you could move in so everybody can sit down, just keep that in mind. But let's go ahead and get started. So we're going to start with Sarah Gabala from Ruhr University Bochum, and she's going to tell us about Anonify, decentralized dual-level anonymity for medical data donation.
Hello, everyone. My name is Sarah Gabala. I'm from Ruhr University Bochum, Germany, and I will present to you our work, Anonify decentralized dual-level anonymity for medical data donation. So medical data donation is a voluntary act where individuals share their medical data with researchers to support scientific research. Medical data donation has gained a lot of attention recently, especially during the corona pandemic, with many applications have developed to facilitate data donation. However, medical data donation faces challenges, especially due to the sensitive nature of medical data. So to encourage users to donate their data, we need to ensure privacy to them. K-anonymity is known as one of the most popular privacy protection methods. It ensures that each individual cannot be identified from K-1 other individuals. So to achieve K-anonymity, a data set should be modified to by removing direct identifiers like names and generalizing quasi-identifiers like age to create groups of users who are similar in terms of quasi-identifiers. And by doing this, we protect sensitive attributes, like here in our example, disease. One of the main advantages of K-anonymity is its ability to allow flexible analysis, so it doesn't assume exact usage or the exact studies that the researchers will conduct. And of course, this is good. However, K-anonymity requires a central trusted aggregator. That means the user should trust one entity for aggregating the data and also for learning who donated what. Another problem with K-anonymity is its vulnerability to attribute disclosure attacks. And so as we can see, and the second group here, that all records have the same disease. So if an adversary knows that specific person has a record in this group, then the adversary can know that this person has HIV. There are solutions for this issue. However, these solutions still require centralization. To address these limitations, we propose our protocol, Anonify. In our protocol, the responsibility of the aggregator is distributed over several servers, where one of the servers should be honest. Anonify achieves privacy protection at both the communication and data levels, so it achieves dual-level anonymity that ensures users can be linked to their donated data through communication metadata like IP addresses or through characteristics in the donated data itself. We assume a global adversary who can observe the whole communication, and also this adversary can collude with servers responsible for aggregation or researchers. Additionally, it can have background knowledge about some users. In our protocol, we use distributed point functions. It's a method for enabling anonymous writing in a distributed database without servers linking user to specific messages. So to write a message in this database, the user should generate several secret shares and distribute these shares to the servers, where each server gets one share. The server should add the share to its database instance. Then after collecting or processing requested from several users, the servers collaborate together to compute combined database and reveal the written messages. For data anonymity, we rely on two methods, key anonymity and stratified sampling. We use stratified sampling to address the limitations of key anonymity. Both methods are executed within secret sharing settings. So stratified sampling, it ensures that an adversary cannot determine the presence of a user's record in a published data set, and that is by deleting fixed number of records from each group. That adds a level of uncertainty. Our approach consists of two phases. The first phase, registration phase, where the users send their personal information, the quasi-identifiers values, and then the servers collaborate together or work together to apply key anonymity to these identifiers, and then they create classes, broadcast the information about the created classes to the users, and then each user determines the related group. After users complete the registration phase, they move to the publishing phase, where they share their medical data, of course, using DPF, also alongside with the group ID. Then again, the servers work together to apply stratified sampling, but before decrypting the database. So they agree on which rows should be deleted from the database instance, and then they combine the database instance to reveal the sampled or the anonymized data set. And finally, the aggregator publishes the sampled anonymized data set to researchers. In our evaluation, we use a public diabetes data set, and we use ERX for key anonymization, because based on our evaluation that ERX provides better utility than other methods. And for the key value, we use 250 because also as shown in the results here, it maintains good utility, and of course it ensures big anonymity set. We assess the likelihood of linking a specific record in the dataset to a targeted user, and as shown in the results here, all the anonymized datasets have very low values that indicates strong anonymity and low re-identification risks. Also, we assess the performance of machine learning classification algorithms on the datasets anonymized by our protocol, and as you can see, the accuracy of the anonymized datasets are close to the accuracy of the original dataset. Also, another thing we assessed the impact of anonymization on the data distribution. Again, here the anonymized datasets resemble or closely resemble the original dataset. So in conclusion, we proposed Anonymify. It's a decentralized protocol for medical data donation. It ensures a strong anonymity protection without relying on a single entity. According to our results, Anonymify maintains data utility, so it ensures that machine learning algorithms perform nearly as well on anonymized datasets generated by the protocol as they do on the original dataset. If you would like to know more about our paper, because we provided more results, also we provided detailed security analysis, so you can read our paper. Also, we provide the artifacts, so you can check it. Thank you.
Okay. And yeah, we have time for questions. And just raise your hand and they'll bring a mic to you. You can take my mic.
self-progression. I'm wondering about is there only how to say is only one person will be represented as a one record because consider for the comorbid or something, so the disease will be what kind of a disease will be recorded. And finally, the most interesting about is the why you do the stratified sampling, especially the different different subgroup. You have the different disease distribution. So how did you consider this this kind of impact? Thanks.
So you mean that each user will have only one record? Yes, but also we support multiple iteration. So the user can submit at a different interval of time. But using stratified sampling, we prevent an adversary from being sure that the user has a record in this dataset.
Okay, and we have time for more questions. And yeah, let us know if there's any questions online.
Is it all? Okay. I have one question. In your overview slide, you showed that at some point data is decrypted, but I did not see where it is actually encrypted in the first place. Can you explain?
Because I mentioned. So here, as mentioned, they submit their data using DBF, and that means that it's a secret sharing based protocol where data is shared. So it's decrypted.
Okay. I don't see any other questions, but I had a question about the distributed point function. So can you say more about the, because I remember in the paper, there were more details about how that happens, like actually over the network with anonymity and everything. Can you say more about that?
You mean the performance or for the anonymous communication aspect?
Yeah.
Yeah, so we didn't provide this, but we provided some information about this in the in our paper. So according to many papers, DBF doesn't lead to high latency, and this is good. Although we don't really care about latency here in this context because this scenario can tolerate some level of latency. Another thing, which is the bandwidth overhead. And we provided some details about the bandwidth overhead. And since the user don't send many messages or they don't exchange many messages, still the overhead is limited. But it's related somehow to the database size. So if you are interested, you can read more about this in the paper.
Okay, and we have time for one more question if there are any more questions. But if not, let's go ahead and thank Sarah one more time. Yeah, great talk. Thank you. And so the next talk will be Wei Sun from Duke University. The title is SLK Secure Human-Centered Wireless Sensing. And this talk will be online, but the speaker is also online, so there'll be an opportunity to ask questions. And with that, I'll turn it over to the video.
Hello, everybody. My name is Wei. Today, I will present a systematization of knowledge paper on secure human-centered wireless sensing. So in the past few years, we have been seeing the proliferation of human-centered wireless sensing systems for human gesture recognition, indoor human localization, human activity recognition, and even using the wireless signals to detect the human identity. These human-centered wireless sensing systems can consist of 4 important modules in deep learning area. For example, the data sensing modules with different kinds of IoT sensors, such as a wearable mobile device, Wi-Fi access point, to sense the human private information. And then the data processing module is mainly aiming to extract the wireless channel, do signal processing on the wireless channel, and design advanced algorithms to extract the characteristics from these wireless signals. and then use them as the input of machine learning models such as deep neural networks to infer the human private information, including human body health, behavior recognition, human-computer interaction, and even detect and even explore the Internet of Things security and privacy from these wireless signals. However, the data sensing, data processing, and data representation with machine learning models are vulnerable to cyber attacks, which will help the attackers to steal the human private information from this signal processing pipeline in human-centered wireless sensing systems. As a result, these systems will introduce a privacy leakage threat, such as the human location privacy has been stolen, human living habits have been stolen, some behavioral biometric characteristics such as walking pattern, heart respiration rate, sleep stage, and gestures have been stolen from these wireless signals to predict the human identity. So we try to systematize the knowledge of the human-centered wireless sensing systems by evaluating, systematizing, and contextualizing the existing knowledge of human-centered wireless sensing systems from the security and privacy perspectives. Our contributions are threefold. First, we show the taxonomy of wireless signal processing in the privacy attacks and defenses through the tables and paper surveying. And then we identify some practical challenges in deploying these human-centered wireless sensing systems to extract and infer human private information in deep learning era. And we identify the design space towards the privacy-preserving wireless sensing systems, not only to help the people to extract the wireless signals and thrive the human lives, but also protect the human private information. So the threat model of the privacy attacks are as follows. The attacker's goal is to steal the human private information from the wireless signals, including location, living habits, behavioral biometric characteristics. And the attacker's capability is to sense the types of wireless signals and deploy the corresponding wireless receivers to receive the wireless signals and analyze them for attack. So we propose a signal processing pipeline to characterize the human-centered wireless sensing systems that have been attacked by the attackers. The attacker just need to deploy a eavesdropper, a wireless receiver to snoop the wireless signals. These wireless signals will go through the wireless channel estimation module. This module will include the wireless channel modeling, channel estimation. With the estimated wireless channel, we can extract some important characteristics from the wireless channels through the signal processing functions, such as leveraging the signal attenuation, Doppler shift, time of flight, angle of arrival, or angle of departure to characterize the wireless signals, and further use mathematical model or machine learning model to infer the human private information. For mathematical model, we can have triangulation. For location identification, filtering. For signal processing, human hidden Markov model to model the wireless signals affected by the human body, and a dynamic time ramping algorithms to process the wireless signals for accurate inference. And also we can use some machine learning models, including conventional machine learning models, such as k-nearest neighbors, SVM, and so on and so forth. We can also leverage the deep neural networks to characterize and identify the human private information from the wireless signals that have been widely used in the existing or state-of-the-art wireless sensing systems. Based on that, we propose a table to present the taxonomy of existing inference attacks for human private information prediction, which will include attack goal, privacy leakage, wireless environment, attacking device, and the wireless signals that have been snooped to predict the human private information, and how we will infer the human private information based on machine learning or mathematical models. And also we characterize this human-centered wireless sensing systems characteristics or properties based on the cost of deploying this attack and what kind of wireless technologies have been used to resolve the multipath, to process the wireless signal accurately, to extract the information of interest. And also we divide the papers into active attacks and passive attacks, depending on the stealthiness of these attacks. Also, we propose the defenses that can against the privacy attacks in human-centered wireless sensing systems. These defenses have been widely studied in the existing papers for human-centered wireless sensing systems based on prevention-based defense and detection-based defense. For the prevention-based defense, we can have the geofencing. Basically, we can isolate the wireless signals transmitted from the transmitter to disable the attacker, and we can do nulling at the transmitter to steer the wireless signals to the different direction where the attacker is not there to disable the attacking. And we can randomize the wireless signals transmitted at the transmitter to disable or for the attacker. And also we can deploy extra radio frequency receiver to jam the attacker's received signals. And also we can use the multiplex relay, phased array, or meta surface to obfuscate the wireless signals which have been received at the attacker to disable the attack. For the detection-based defense, we can have a detector that can actively transmit the wireless signals towards the attacker and analyze the reflected off signals from the attacker to detect the existence of the attacker. We can also do the passive sensing by eavesdropping the electromagnetic emanations from the attacker to detect the existence of the attacker. And since this attacker could be plugged into the socket on the power line, so we can do some side channel information to analyze the energy consumption from the power line to detect the existence of these eavesdropping devices deployed by the attacker. So we identify some open challenges to achieve privacy-preserving human-centered wireless sensing systems. First, how we can deploy the sniffing device at the attacker to accurately monitor the wireless environment for the attack, and how we can compensate the hardware imperfection and artifacts to accurately extract the characteristics from the wireless signals for the attacker. And also, the machine learning model have been widely used to accurately infer the human private information, but these machine learning models are vulnerable to the cyber attacks, especially in the adversarial machine learning have been widely used in recent years. Also, how we can resolve the multipath in dynamic and multipath, multi-person environment, which is a great challenge. Also, not only we want to enable the legitimate sensing, but also we want to disable the attacker and preserve the wireless communication for the existing wireless communication infrastructure. In the future, we would like to apply trustworthy machine learning models to accurately and safely infer the human private information without any leakage. And also we want to deploy some privacy guarantee to build the defense techniques and systems for the privacy-preserving human-centered wireless sensing systems, and also how we can secure the multimodal sensor fusion-based inference attacks to steal the human private information. With that all being said, I'm happy to take any questions.
Speaker hand. Okay, I'm not sure if the speaker's online or not. They're not. Yeah, so yeah, the speaker's not online, but if you have questions, there's an email address on the paper. And then if anybody has any comments, then we're happy to take comments too. If anybody has any comments, related to the paper. Or... Okay, yeah, so if you do have questions, there's an email address on the paper. And then right now is Birds of a Feather sessions in this room and the next room. And so take a look at the program and you can see the different birds of a feather sessions that are happening. And thanks for coming to the session.
Well, hello everyone. I'm Sylvain. Welcome to this MPC session. We're going to start off with Tamir, who's going to present the multiple millionaires problem.
Thanks. Speak about new algorithmic approaches and protocols for the multiple millionaires problem. And this is a joint work with, now why doesn't it work? It worked a second ago. Just a second. So that. Oh, thank God. Okay. It's a joint work with my colleague Avishai and I. Okay, so we are going to speak here about two very fundamental problems called the maximum problem and the multiple millionaires problem. In both inputs, in both problems, the inputs are private integers x1 to xn, and let's assume for the sake of the discussion that they are secret shared among k parties, even though it is not a limiting assumption for our case. This is just for, we have some ground to stand on. And in the first problem, in MaxP, the desired output is the maximum for those inputs, while in the multiple millionaires problem, the desired output is the indices of all inputs that equal the maximum. Now, those are fundamental problems which are natural extensions to the very first problem of multi-party computation that was introduced by Yao in 1982. And each of those problems is reducible to the other. So in some protocols, I will solve the MMP. In some, I will solve the MaxP, because once you solve the one, you can then go to the other. And we should focus on protocols that have information theoretic security. So such problems have many applications. For instance, in privacy-preserving machine learning, it's relevant for k-means clustering or nearest neighbor, where here we want the minimum, not the maximum, but of course, maximum, minimum, almost same, and or softmax in neural networks. And in other privacy-preserving applications, it's relevant for auctions, voting, or fingerprinting matching. Okay, so we should describe here 4 approaches to solve those problems. Tree-based protocols, a monotone representation protocol, I'll explain it once I get there, digit decomposition-based protocols, and binary search. So the first approach is to use a tree-based protocol. So here we have the, let's say, 8 inputs, and the idea is, by the way, this idea I presented here for binary tree. It was already done in 2 previous works. The idea here is to simply compute the maximum between every 2 pairs until we get to the root of the tree, which is the maximum of all the inputs. And here we need to somehow securely compute the maximum of two nodes, of 2 values. So we base our computation on this very trivial identity that max of A and B are A plus equals A plus the bit which equals 1 if and only if A is less than B times B minus A. So if A and B are protected in some manner, let's say by homomorphic encryption or by secret sharing, as I assume here, I will not dig into the details how to compute this securely. Actually, this talk will be almost cryptography free, because we want to focus on the high level, on the logic of the protocols, and we should not open up the black boxes of how to perform the secure computations, like here, comparison or multiplications, and you can look it up in the paper. Now, this approach can be also taken when the tree has higher degrees, let's say m degree 3. So here, if m equals 3, we can do this computation until we get to the root, and then we get the maximum. So here, we have to somehow, the building block will be to compute maximum of, in that case, 3 secret values, A, B, and C, and because m equals 3 here. And how should we do it? So there are several possible approaches. Or we can use an all-to-all comparison algorithm that compares all pairs in that set of m values. And that, if we do that, we should get a round complexity of 1, which is minimal, but the size will be maximum, to be O of m squared. On the other hand, we can apply here the binary tree approach, which offers a minimal size of O of m and a round complexity of log m. So this is up to you how to open up this little box of computing the maximum among M inputs. So this is how the round complexity of the tree-based protocols depend on M. If we take M, which is a constant, we shall get number of rounds, which is O of log N. If we take M to be some root of N, the number of inputs, we should get a constant number of rounds. Of course, there is a trade-off, which is very, very clear here. Okay. Next, we shall move to another protocol, which I call a monotonic representation-based protocol. Here we have only one single protocol. It is designed for inputs that are drawn from a small domain, a very limited domain. And actually, we should use it only as a subroutine in our next protocols, so which are digit-based protocols. So let's assume that each input is taken from some small domain, 0 up to q-1, and we shall represent it by a monotonical representation, namely by a sequence of q-1 bits. And instead of focusing on the equation, let's just take an example. If q equals 5, we have 5 possible inputs, 0, 1, 2, 3, 4. And this is how we present 0. This is how we present 1, 2, 3, 4. Of course, the number of ones equals the value of the input. Now, if we do it this way, then in order to compute the maximum, we simply have to go over each of the columns and then take the OR of the private bits in that column. Now, the beautiful thing is that to compute an OR of n bits, that can be done in a constant number of rounds, independent of n. And that is why that protocol has a constant round complexity, both in the pre-processing stage and in the online stage. It does not depend on n. So let's take an example. Suppose that we have q equals 8, and there are 3, n equals 3 inputs. So this is 5 is encoded this way, 3 is encoded that way, 6 is encoded that way. And then if we go column by column and take the OR of the bits in each column, we should get here the monotonic representation of the maximum, which is of course 6. Very, very simple. As I said, the main purpose of that protocol is to serve in what comes next. So what comes next is 2 protocols which are based on digit decomposition. We should start with a binary decomposition protocol. And that protocol, as opposed to the 2 that we had before, will solve directly the multiple millionaire problem, not the max problem. Namely, it will not, if the tree-based things, protocols or the monotonic decomposition first computed the maximum, and from there, the identities of the richest or the largest inputs, here we go directly for the MMP problem, and it uses the bit representation of each of the inputs. So suppose that capital B is an upper bound on log 2 of all the inputs of the maximum. And of course, each input can be represented binary by B bits, and that protocol scans the inputs bits from left, MSB, to right as follows. It does this computation from B-1 position to 0 position. It computes some control bit that we call it SB, using that formula. And that control bit decides how we shall update the bits in the next column, namely when we go to the left, either by this update procedure or by this update procedure. And we claim that if we do this computation properly, and then what we shall be left with in the rightmost column are exactly one in all the lines, in all the rows in which we had an input that equals the maximum L, and the proof of that lemma appears in the paper. So let's do a very, very swift demonstration, even though I don't expect you to follow the details, but just to have an idea what's going on. So suppose we have 4 inputs, 11, 7, 10, 11. They can all be represented by 4 binary bits. And here you can see the binary representation. I marked by yellow the 2 inputs which I'm looking for, the maximal inputs, this one and this one. What we do is we start with the leftmost column, we compute SB, which is the OR of the formula was a bit different, never mind now, it's 1. And since it is 1, the value of the bits here are updated by the formula that we had in last slide. The details are not important right now. Then in the next column, we get SB equals 0. We get here that kind of update, and so forth and so forth. And at the end, you have to believe me, what we get is the one in that row and that row. Of course, all the computations of the SB bits, all the computations of the OR and the if, then, else, everything must be done in a secure manner. And we explain in the paper how to do it securely without leaking any information. These are, as I said, information theoretic secure protocols. Now, so these are the maximum, the two maximal inputs as we wanted them to be found. Next, we should discuss an extension to using larger bases. Let's say Q equals 2 to the power of D. It's more convenient to use a base which is a power of 2. So here, it scans the Q digits of the inputs from left to right, and it issues at the end the indices of the maximal inputs. So in spirit, it is similar to what we had in the binary case, but the details are a bit more complicated, not truly, but there's more substance to the details here, and I encourage you to look in the paper to see how it works, but in spirit, it is the same thing. And here, we need to compute in each column of digits what is the maximal digit that appear there. And for that purpose, we use the constant depth max-speed protocol that we showed 4 or 5 minutes ago. So that one is used here in order to compute the maximal digit in each column, and then to decide how to update the digits in the next columns in a manner which resembles what we had in the binary case. And I should say that the size of the protocol grows like 2 to the power of D over D, where D is the number of bits in each digit, while the depth number of rounds decreases like 1 over D. Of course, there is a threshold between number of rounds and, between the size and number of rounds. That's it. Next, the last protocol is based on the work of Agarwal, Mishra, and Pincus from 2010. They devised an MPC protocol for securely computing the k-ranked element in a distributed database. Now, we saw that we can use that protocol in order to solve also the maximum problem. And so basically, it boils down to a very simple thing. Given an a priori upper bound B on M, we have to assume something that, as we assumed in the previous protocol, that we have some upper bound on the number on the values of the inputs. Here too, we assume some kind of upper bound. Then the protocol boils down to a binary search over that interval, where's the trick? Where the decision between continuing the search in the lower half or the upper half must be done in a secure manner without revealing information on the inputs to none of the parties. So that's about it. Now let's summarize the results. We conducted very, very detailed analysis, theoretical analysis of those protocols regarding the round complexity and size, both in the pre-processing stage where you still don't need to rely on the inputs, and also in the online phase after the inputs were revealed. And we also conducted experiments where the cryptographic computations were done by secret sharing, as I mentioned in the first slide. And what we get here is this trend. The 3 protocols are the ones that have the highest number of rounds, but the lowest size, where here you have the binary tree. Here you have a 3, 4, 5 degree tree. Of course, the more we increase M, we go back here. Those protocols depend on the upper bound on the value of the inputs or on the maximum. So we have here the binary decomposition, the queue-based decomposition, and the interactive binary search protocol. And this is roughly the trend between those 3 options. And those protocols have a constant round complexity, either if we use a tree of degree, which is of square root or any other root of n, or if we use the monotonic representation. But of course, the price that we have to pay is in the size of the computation. And I believe that that's it. Thank you very much.
Well, thank you, Tamir. Do we have any questions for Tamir? Do we have any questions online? Oh yeah, question here.
So on the previous slide you showed, well, you said computation, but it read communication. So for the horizontal axis, you said computation.
Yes.
But it says communication size.
No, it is communication size. How many bits are exchanged?
So it's not. But and what is the computational complexity? How do they compare there? So every round is the same complexity.
We count the time complexity in terms of rounds. This is the most influential parameter. And in size, we mean how many messages or how many bits you have to exchange between the parties in doing that computation. So it's space versus, this is time in that sense.
Yeah, although okay, sure. Roughly, sure.
Yeah, thanks, Tamir, again. So now let's have Mariana, who's going to talk about how to compile secure computation protocols from passive to active security beyond arithmetic circuits.
All right, hello everybody. This is joint work with Dennis Murphy and Chen Gan, both of whom used to be at University of Buffalo, but Chen graduated now. He is working at Meta. So as part of this talk, I'm going to be talking about secure multi-party computation in general. And this is a way to actually transition from passive or semi-honest security to a malicious security. And we're going to primarily be in the setting where we use secret sharing. And so just to, get you in the framework, right? So the solution that we're developing applies to any type of computation that somebody might be desired to do. So we're just thinking about there are certain participants that have private inputs. They enter their inputs in the computation. And in this case, I'm saying using secret shared form. There are some participants who are going to be running the computation, and then the results get delivered to one or more parties who are going to assemble the results. So for the purposes of this fork, the exact computation is not necessarily important. We're looking at the general formulation of this problem. And so when we started looking at this, we're primarily looking in the setting with the honest majority, which means that there is the total of n participants who are running the computation, so that there are computational parties, and we require that, less than half of them are corrupt, right? So the majority of the participants have to be honest and not colluding with each other. And so this is something, or this sort of compilation from, passive to active security is something that's been around for some time and started in a way with the sort of the concept that we're, using was started with speeds, and there's other work that follow, but in the context of honest majority setting. So what we have is that we start with the building blocks that were shown to be secure up to additive tags. We're looking at elementary operations such as additions and multiplications and in arithmetic circuits, where the only error that an adversary can introduce is an additive error. So this is something that's been shown before, for the protocols that we typically consider. And the way this proceeds is that we run computation on shares the way we would. So this square bracket notation means that the values are secret shared, they're protected. For inputs, the intermediate results, everything. So we execute one thread the way we would, and then we execute another branch where everything is randomized by a global private value, a random value. And the idea is that you evaluate two of these branches, and before you can disclose any results, you will make sure that they're consistent between each other, right? So the purpose, So the purpose of this random number is to ensure that if the adversary tempers, one of the branches, that it won't be able to tamper with them consistently because of the secret is something that they don't possess. That's the idea, right? So this is where we started. And when we started looking at this, the issue that we came across is that the idea or the security analysis in this dual execution framework was presented in the case where we have arithmetic circuits that have only two gates, addition and multiplication. But when we start using them in practice, the efficient protocols that were developed have actually more elementary operations than only these two operations. And I would like to look at as a simple example of comparison that is somewhat difficult to do in the setting, right? It's ubiquitous, but we'll need to be able to realize it in this setting. And so what we have in this case is that I'm using the example of a comparison, so less than. And typically the way it's realized, and you have two arguments A and B that you'd like to compare, you compute the difference and you compare the difference to 0, right? You want to know if the most significant bit is positive or if it's 0, 1. And so typically the way it proceeds is that we produce a number of random bits, we create this random mask, we add it to the private input that we have, we open that protected value, at which point we have access to the individual bits, and we continue computing on the individual bits, which is going to be faster because the comparison operation actually, what we need is actually, we need to look at the most significant bit, right? We need to determine the most significant bit for this operation. And so the issue in this case is that somebody analyzed an arithmetic circuit, but what we actually use is not a pure arithmetic circuit. And so where we, sort of started this work, we say, okay, we need to determine the set of gates, elementary gates that people might use in an operation. And for the purpose of this talk, we're focusing on field-based computation, something like Shamir secret sharing. And so in this case, if you look at these two in the middle, there are addition and multiplication, but there's also two types of randomness that can be generated. This random element of the field and also a random integer of a specified bit length can be produced for statistical hiding. So the first one is going to achieve perfect hiding. This one is for statistical hiding where you would like to avoid wraparound. And also that there is an open gate, which is fundamental, right? It's used often. And mulpub is primarily for efficiency reasons where it can do multiplication and open at the same step and is going to have better performance, but fundamentally it's not changing the functionality, right? It's for performance reasons, and this is why I'm saying it's optional. All right, so where we take this is that we sort of analyze the logic of the, the setting, and we show that it's not always safe to delay verification until the very end before the inputs get disclosed. And, intuitively, it makes sense. For example, if we look at, say, statistical hiding that uses integers of a particular side, if the adversary was able to tamper with intermediate results and, say, inflate the input, the private value that is supposed to be short, and we use statistical hiding to protect it, now it's actually not guaranteed that the value is protected, right? So we have some additional examples in the paper, but intuitively, if somebody tampers with the intermediate results, it doesn't mean that like when we open, we can disclose information about those values. And so where we take this is we, modify the solution, we create our own compiler from passive to active security. And the way it works, there's a couple of different steps. So the first thing that we needed to do, we treat this as an extended circuit that has, in addition to addition multiplication, has some other gates. And we analyze under what circumstances it's safe to call an open functionality. And intuitively, sort of you can think of if I'm only generating randomness, say I want to generate random bit and I'm opening, it's not possible to reveal anything about private inputs. In this case, so it would be safe to proceed. But in some other cases, it's actually not safe. And we present an algorithm where we analyze the computation and say, you have to inject verification at these points in the circuit. And then what we need in addition to that is we also need to demonstrate that, our construction in this semi-honest model in the passive security is secure up to additive attack, because this logic assumes that you have to have security up to additive attacks. And this is somewhat complicated. It also has like a couple of different steps. We need to re-examine the notion of linear protocols, which were addition and multiplication before. We showed that others are also linear, except that open. We couldn't show that open is secure up to additive attacks, so we sort of treat it separately. And then we formulate the notion of extended linear-based protocol that combines all of the different gates that we have. We'll look at specific instantiations of the gates that we have. We prove them up to secure up to additive attacks. And now we have the starting point where this extended circuit is secure up to additive attack. And at this point, we're ready to proceed with a compiler that uses this notion of dual execution when we run one branch and we run a randomized branch. And we also basically inject verification at the places where our algorithm said you have to verify prior to opening. Open is a special case. We basically need to use the version that is secure up to malicious attacks, because it cannot be secure in the setting of where we require that it's secure up to additive attacks. And so in this context, we obtain this compiler that starts with a version that is secure up to additive attacks. We use open gates that are secure against malicious behavior, and we sort of check in more places than just at the end. All right, so what I wanted to show at the end, so obviously the details are in the paper. There's proofs. It's a little bit tedious to show different properties, but what I wanted to demonstrate that we haven't seen in previous works that are similar is the gap between passive and active security. So on this slide, what we have is how many operations are run in a batch at the same time, and we'll look at different operations. These are addition, multiplication, comparisons, less than, equality, and this is over the threshold Euclidean distance, which is basically that product followed by a comparison. And so in this case, this is the size of the vectors. We might want to look at, say, 1,000 of them executed at the same time, because if you execute it only once, then the latency is significantly impacting the performance. But if you see, looking and say this column is that active security is about 2 to maybe 3 times slower than what we have in the presence of just passive security. So the gap between these two is actually very small these days. All right, so I think I'm out of time. I would like to conclude and say that this work's been in the context of field-based computation, such as Shamir secret sharing. But because there's been like a lot of push to operate over a ring, which is sort of native to the CPU instructions that we're using, that would be significantly faster. And as a part of ongoing work, we're also looking to modify that to the ring setting, to the decay, where we need to slightly change the gates that we consider, but overall transition is going to be similar. All right, thank you.
Well, thank you very much. Do we have a quick question for Marina?
Thank you for the talk. What happens in case the entire circuit that we are doing calculating is deterministic but not random? Do we need to inject verification steps in between them?
If you're not using open, right, so everything is deterministic, then you wouldn't be able to protect with randomness in open. Open, fundamentally open is the problem, right? If you're not calling open, then you can proceed until the end.
Okay, thank you.
Do you want to go really quickly?
Mm-hmm. It's still as before, the difference is the stronger analysis that proves that it actually works with the new gates. Cool.
Yeah. So, you can use dual execution, right? We're just saying that you need to be checking more often than just once at the end.
Okay, thanks to the speaker again.
One question online.
Right. Next, we've got Nirajan. So we've got Nirajan, who's going to talk about summation-based private segmented membership tests using FHE.
Okay. Hello, everyone. I'm Nirajan. Today, I'm going to present this work. And this is a joint work with Jonathan Takeshita, Jeremy Stevens, and Taeho Jeong, and all authors, including myself, are from University of Notre Dame. So firstly, I would like to go over this cryptographic primitive called private membership test, where we have a receiver who holds a query element Y and a sender who holds a set, let's say X. So in private membership test, receiver basically tries to see if the query element is contained within the set X. Some requirements are the sender should not be able to learn anything about the query element Y, and the receiver should not be able to learn anything about the elements of the set X. In this work, we extend this problem to a new problem called private segmented membership test, where instead of single sender, we have a multitude of senders. And the receiver is basically trying to see if the query element Y is contained within the union of these sets instead of a single set. Some new requirements that we add are both the receiver query and the sender set should be encrypted throughout the whole process. We should maintain provenance privacy. That means basically the receiver should not be able to learn whether the query element is coming from any of the individual sets. The protocol should be able to tolerate a high number of senders, potentially thousands, and we operate in a semi-honest setting. Some applications of PSMT problems are some basically tax authorities trying to see if any tax evaders have accounts within domestic or foreign banks, which can be thousands, and banks themselves trying to screen customers before extending any kind of loans or other kind of services, and even government entities trying to work together to work on encrypted databases to protect personally identifiable information of the customers. Some existing solutions that can be used to solve the PSMT problem include private sender intersection, private multi-party PSI, or even private membership test that we discussed earlier. Many of these solutions work excellent in the specific scenarios, but for the PSMT problem, they lack in many ways. First of all, they lack scalability for a very high number of senders. Most of them also lack provenance privacy or provide provenance privacy as a very high cost. And finally, they require the senders to access the sender sets in plain text for the protocols to work in an efficient manner. Now we go over one of the existing protocol, which is based on FHE. So basically, in this FHE-based protocol, to test if a query element Y is within set X, the receiver will send the query element encrypted to the sender, and then sender will compute this polynomial over here, which is basically the multiplication of all the differences. And you can see here the sender set element is in plain here, and after computing this polynomial, will multiply with the random element and send it back to the receiver. Now receiver will basically see if the result is 0 or not. If it's a 0, it will conclude there is an intersection, otherwise it's not an intersection. Now in this simple problem, we can see that there's a fundamental limitation. There is the annihilating element of this polynomial is 0. So if the number of senders increase, that means we'll increase the multiplicative depth in FHE in a logarithmic fashion. So this brings us to our new idea, which is basically to compute this polynomial, which is kind of like inverse of the previous polynomial that we saw. And in this, you can see the annihilating element is now infinity instead of 0, so that after the computation of the polynomial, we can add them together instead of multiply. That means the multiplicative depth remains constant and it doesn't explode, and we save efficiency. So some challenges for this new idea are basically this division operation can be very costly in FHE. Also, the idea of infinity does not exist in FHE. We cannot compute it, so we need to find a function to actually approximate this kind of behavior, and also be able to approximate this function on a very large domain, so we can work with large sender sets. This takes us to value annihilating functions, which is basically a function that maps 0 to any large value, let's say k, and any other values to 0. So if you see here, E tan is a VAF here, which takes an input, And then after computing E10, we can basically submit all the results together and see there's an intersection if the result is K. If there's no intersection, if the result is not K, then there is no intersection. Now we can see that there's a branching operation happening here, which makes it very hard to compute in FHE. So we need to approximate this function. And we found that derivative of hyperbolic tangent shows preferred qualities that we need to for our VAF. However, just using simple techniques like Chebyshev to compute the derivative of hyperbolic tangent over large domains turned out to be very expensive. And also it wasn't very accurate over the range that we wanted to. So now to solve this problem of the high domain, we use domain extension polynomials. So domain extension polynomials basically shrink a large domain into a smaller subinterval so that the property of VAF around 0 in the subinterval is preserved. So in this image, you can see this, the black function is basically reduced into this smaller domain, into this red function, so that all the edges are mapped into the edges of this red function, and the accuracy within this interval 0 is preserved. Now, some other addition that we added for our protocol was basically adding some random masking numbers so that the server's items cannot be inferred by the receiver. And instead of using simple FHE, we use threshold FHE to make sure no single party holds the master key, and if only enough parties are using the protocol, the result can be decrypted. And we also applied noise smudging techniques to make sure the threshold FHE itself is not susceptible to INDCPAD attacks. Other optimizations that we enabled in the protocol was the regular one FHE batching, where we, instead of encrypting a single vector, we encrypt a multitude of vectors together to increase the throughput. And to reduce false positive, we use this technique called square and scale to eliminate any contaminated value that can result in false positive. And we also did some parameter exploration to provide optimal parameters for the DEP and Chebyshev to work with large sender cells, which are provided in the paper. So the final protocol looks like this, where we assume the receiver and the senders are given partial decryption keys, encryption keys, and homomorphic evaluation key. So first, the receiver will encrypt the query and transmit it to the sender. Then the sender will compute the difference and apply the DEP process, and then evaluate the VAF function, which is E10 over the difference using Chebyshev approximation, and then apply the homomorphic squaring and scaling techniques to eliminate any kind of contaminated values. Finally, a leader sender will basically summate all the VAF values from individual senders, add a random non-zero element R, and then send it back to the receiver and the senders. The senders will partially decrypt summation and add a smudging noise to make sure the INDCPAD security and send it back to the receiver. Receiver will finally decrypt the summation and combine it with own share of the decryption, and then confirm an intersection if the summation crosses the threshold tau, and deny it if the summation doesn't crosses the threshold tau. So going over to the evaluation, we implemented our protocol and Kong ETL with multi-party support using OpenFHE, and done comparison with these three works. We employed the CKKS parameters in our protocol to ensure a 120-bit compilation security and 36-bit statistical security. For the scalability testing, we saw that for a small number of senders, our protocol was slower than compared to other protocols because we were doing some approximation, which requires some FHE depth in the smaller setting. But we saw that for a higher number of senders, our protocol started to become more efficient, and almost 5.6 times efficient when we extended it to almost 4,000 senders. In the figure below, you can see for individual operations, our protocol was again slower than the other state-of-the-art Kong protocol. But for when we take the total time into account, which also include the aggregation time, the multiplicative aggregation nature of Kong ETL starts to slow down their protocol, which is in the red, and our blue here, which started to show speed up. Similarly, for the overall computation and communication, we did experiments for high throughput network like 1 Gbps and 10 Gbps, and we saw similar results for a small number of senders. We saw that our protocol was slower than others, but when we increased the number of senders, our protocol was almost 2.4 times faster than the other protocol. So in conclusion, we introduced the concept of PSMT to query a set segmented across many data holders. enable various optimization, and also ensure IND-CPAD security in the protocol, and demonstrated a very high scalability for a very high number of senders. In the future work, we would like to support multiple query items for a single query, which is very similar to PSI, and also reduce the communication overhead, which is being generated by computing on encrypted data right now, and also enables receiver-side batching, and also change the setting to malicious PSMT so that we can handle malicious adversaries. Thank you for listening to the talk, and I'll be ready to take any questions.
Well, thank you. Do we have any questions for Nirajan? Yeah, in the front.
You were saying that you add some small random masks to hide the difference, and I didn't quite see it in the protocol description. How do you decide how large those masks have to be?
You mean this mask, the R?
So I'm not sure, because for that R you said it was to prevent the IND-CPAD attack.
Oh, there are two masks being added here. So the one for IND-CPAD is the smudging noise, and one, this max, which is to make sure the receiver cannot infer anything about the sender's elements if it just gets the plain approximation.
Right. So how large is that R?
Oh, the R is computed within the interval so that it doesn't contaminate the values, so that the intersection, we make sure the intersection always crosses a certain threshold, and the R is very small bound, and then we make sure the R always lies within that bound so that we don't get any false positives.
But does that allow you to give any security guarantees, like if it's really, really small?
It's small in a sense that it allows us to just allow the receiver to not infer anything about the sender elements, and does not contaminate the overall summation, so that when there's an intersection, it still crosses the threshold value.
So I guess my question is, how do you make it small enough that it doesn't taint the final result, and large enough that it does hide the difference?
Okay. So for that, we did heuristic experiments, and then we found that I think our values were somewhere between, depending on the approximation accuracy and how much degree of polynomial give it to approximation, I think minus 2 to 2, something like that. But it was heuristic based.
Okay, thank you.
We had another question somewhere. Yeah, over there.
Do you support negative numbers? Like, I was wondering if there's something happens, like you have a positive infinity and negative infinity and cancel out, and something unexpected happens.
Negative numbers, as in a sense, so all the negative numbers will also get mapped to very small values. So in a sense we do, but we won't be computing any negative infinity, because the hyperbolic of tangent function can only give you positive infinity or like positive high values. Like over here. So when the input is 0, it will always go to a positive number. So there won't be like.
Oh, okay. I think I get it.
Thank you.
Any more questions? All right, let's thank the speaker again.
Thank you.
So now we've got Sebastian from the University of Stuttgart, who's going to talk about multipass.
Yes, so my name is Sebastian Hasler from the Institute of Information Security at the University of Stuttgart in Germany, and I'm presenting multipass, reduced communication MPC over Z2K. So multipass is an offline phase and Rust implementation thereof for the Speeds MPC protocol. So let's first take a look at the existing Speeds MPC protocol. This is a multi-party computation protocol, and in this talk I focus on 2 parties, Alice and Bob. And the protocol consists of an offline phase where the parties, for instance, choose secret MAC keys. We have seen this also in the from passive to active security talk. This is for this dual execution. And they also compute some other correlated randomness, which I will mention later. And then in the online phase, the actual input-dependent computation happens. So in this computation, all inputs and intermediate values are secret shared and authenticated using the secret MAC key, and we denote this by double brackets. And if the parties want to add up two values, then this can just be done locally. But if they want to compute a multiplication between two values, that's a bit more complicated. And for that, we need correlated randomness from the offline phase in form of so-called beaver triples. A beaver triple is a triple A, B, C of secret values, where A times B equals C. And then this can be used as a mask to mask these inputs to the multiplication and then reveal these masked values, and then the parties have everything they need to compute a multiplication. So though I don't go into details about how this works in the online phase, but now the question is, how can we produce such beaver triples? And because we need one such beaver triple for every multiplication gate, how can we compute many such beaver triples? And how can we do it efficiently? So here, that's again the definition. And of course, there has been a lot of research going on how to do this. There are oblivious transfer-based, linearly homomorphic encryption-based, or somewhat homomorphic encryption-based protocols. Also, these protocols differ depending on what is the domain we want to compute on. So the domain could be a finite field set P for some prime P, but it could also be set to K. And this is what we focus on in this talk because it enables a more efficient online phase as we can use native machine instructions. As you can see here, there is a lot of related work on how to produce beaver triples in these different settings. And I want to focus, or this work wants to focus on setups with a low number of parties. And in this case, this LoGear 2.0 is the most efficient protocol when it comes to the communication required to produce beaver triples. However, as you can see, there's a gap right here because this protocol had not yet been generalized from the prime field setting to the Z2K setting. And this is where my work or our work multiparse comes in. And of course, this is published in PETS2024. So let's first look at a basic building block of this LoGear protocol, which is this linearly homomorphic encryption-based oblivious linear evaluation, so OLE. What is this? OLE means we have Alice's input A and Bob's input B, and we want to compute additive shares of the product A times B. And using linearly homomorphic encryption, this can be done by, the goal is to have additive shares of A times B. So this can be done by Alice encrypting the value A, sending this encryption over to Bob, who then performs computes the ciphertext for A times B minus E, where E is Bob's share. Bob sends the ciphertext back, and Alice has the secret key with which this ciphertext can be decrypted. So she decrypts it and obtains the share D. So now we have additive shares of A times B. Okay, and then in this overdrive LoGear 2.0 protocol, this OLE is used as follows in order to generate beaver triples. So from the offline phase, or from the beginning of the offline phase, we have a fixed MAC key alpha, okay? And then also every party chooses their own share of A and B. So we already have A and B, but we still need to compute C as the product of A and B, and we need to authenticate all these values using multiplication by the secret MAC key alpha. And this is done by using pairwise instances of the OLE protocol in order to first authenticate the value B. So we compute B times alpha and obtain alpha times B. In the actual protocol, we obtain shares of alpha times b, of course. And then we also use an amortized version of the OLE protocol in order to compute 3 more multiplications. All of these multiplications are multiplications by A, which is why it can be amortized. And after that, we have all the values which we need. So we have C as the product of A times B, and we also have all the authenticated values. And in order to check that nobody tampered with the computation, there is a MAC check in the end, which then basically outputs our authenticated shells where we can be sure that they are correctly authenticated. However, as this is only secure over finite fields, such as set P for prime P. If we work over a ring, so let's say modulo 2 to the power of T, then there is an attack due to the fact that we have 0 divisors. So in the OLE protocol, a malicious Bob could add another term of A times 2 to the T minus 1 here. And then in the Logia protocol where this is used, this would then have the effect that Alice gets an additional term right here. And depending whether A0, which is Alice's share of A, is even or odd, this has different consequences. So if A0 is even, so it's a multiple of 2, then that means this is a multiple of 2 to the T, which gets cancelled out, so this attack would not have any effect. And on the other hand, if A0 is odd, then the MAC check in the end fails. So this is a selective failure attack right there, and means that Bob can learn the least significant bit of Alice's share of A. And in a more general form of this attack, Bob can learn multiple of the least significant bits of A. So how did we fix this? Of course, I would not present here if we didn't fix this somehow. So the idea is, first note that we want beaver triples over a domain that looks like this. So here we have set 2 to the k plus s. This plus s has to do with the fact that, with other security reasons, for the max to be secure. But let's say this is the domain where we want to compute beaver triples. And what we do instead is we first compute beaver triples over a slightly larger domain where we have an additional s bits using the protocol, which I just presented. And in this protocol, some of the least significant bits might have been leaked to the adversary through selective failure attacks. But then afterwards, we run our new so-called truncation protocol to cut off these least significant bits of the beaver triple. So we obtain beaver triples over our originally intended domain, and they contain no bits which might have been leaked. So this is then secure. Of course, we also did a security analysis. So in the original Logia protocol, the security analysis was based on the security notion of the encryption scheme, which is called enhanced CPA security. And it was shown that this security notion cannot be achieved over for encryption schemes with plaintext space set to K or set to T. However, we did a slight adaptation to the security game, and we call this 2S enhanced CPA security. And we showed that this is possible to achieve, and that this is a security notion that is fulfilled by the BGV encryption scheme under common assumptions, namely linear targeted malleability. Of course, our original goal was to reduce the communication complexity compared to previous work. So now that we have a secure protocol, we did further optimizations, namely using adaptive packing. We use different packing techniques for different parts of the protocol. Packing here means how are the plain text packed into ciphertext. And here for this part of the protocol, for this OLE, we use a different packing technique than for this amortized OLE. Then also modular switching inside the OLE protocol. Before Bob sends the ciphertext back, Bob applies modulus switching to the ciphertext to reduce the size of the ciphertext. This is only that the size is reduced and we have less communication. And we also use zero knowledge proofs with rejection sampling. I omitted the detail that in this protocol, we also need zero knowledge proofs to prove the correctness of the ciphertext. And we use zero knowledge proofs with rejection sampling here, which also reduces the size of these proofs. And these optimizations together mean that the total amortized communication of our protocol in the two-party setup compared to prior work is more than twice as good as the previous best protocol in the same setting. And we also implemented our protocol in Rust. The only other available open source implementation is the one of Speeds2K. And here you can see that our protocol multipass, which is blue here, can outperform Speeds2K, especially if the bandwidth is restricted, which you might want to do in the cloud where traffic is expensive. And at the same time, of course, the communication cost incurred by Speeds2K, by multipass is way lower than Speeds2K, as we have seen on the previous slide. Okay, so thank you for your attention. Here I also have the link to the PETS publication and the implementation, of course. And now I'm happy to take any questions.
Do we have any questions for Sebastian? Yeah, over there. No, it's for Zoom as well.
Yeah. Will your implementation be incorporated to MP Space framework?
No, it has not yet been incorporated to MP Speeds, and there are currently no such plans. This was up to now purely a research effort, but maybe if some company would be interested in using it, then one could do something like this.
You mentioned amortized cost. What is it amortized over?
Amortized cost per triple produced means we cannot produce a single triple because in the ciphertexts we pack many plain texts, like thousands of them, and also the zero knowledge proofs in the OLE protocol are amortized over multiple ciphertexts. And so we produce Vivo triples in batches of many thousands, and this is why we speak of amortized cost.
Got it.
So we divide the cost by the number of triples produced.
Which zero knowledge proof did you use?
We used a variant of the Top Gear zero knowledge proof, but with small optimization where the number of values that need to be sent is reduced from 4 to 3, and with this rejection sampling idea. Yeah.
Okay, thanks. Well, thanks to the speaker again. So now we've got Sajin, who's going to talk about PRAC.
What it actually are? Oh, there is. Okay, there we go. All right. Hi, everyone. I'm Sajin Shashi, and today I'm going to present PRAC, Round Efficient Three-Party MPC for Dynamic Data Structures, which is joint work with Aditya and Ian Goldberg. All right. So MPC protocols have been studied for several decades, and we're now at a point where computations in the circuit model can be efficiently realized via MPC. The main bottleneck for MPC solutions are typically communication-oriented, so the rounds of computation, the rounds of communication, and the bandwidth overheads involved in these communication rounds. While circuit computations are efficiently realized in MPC, computations in the RAM model, in fact, pose a challenge. And so in MPC, RAM itself is typically realized via distributed oblivious RAM protocols, or DORAM protocols. And broadly speaking, there are two such DORAM types of protocols. There is communication-efficient DORAMs, that like DORAM and FlowRAM, and computation-efficient DORAMs like Raman and 3PCORAM. So in this work, we present PRAC, Private Random Access Computations, a three-party MPC framework in the semi-honest setting for random access data structures. So PRAC extends the state-of-the-art communication-efficient DORAM with implementation improvements and extensions based on distributed point functions. So we take advantage of some interesting properties of DORAM, the state-of-the-art communication-efficient DORAM, that make it well-suited to support RAM data structures. And in particular, our work presents 3 different protocols that are exemplar of data structures with varying degrees of what we call data dynamicity. So in particular, we present an oblivious binary search that is static in nature. That's to say it operates over assorted secret shares of an array of data on an oblivious heap that allows for arbitrary additions but deletions of only the minimum item. So we call this restrictively dynamic. And also the first oblivious AVL tree protocol in the distributed trust setting, which allows parties to insert and delete and look up in this AVL tree without any party realizing the items or the shape of this tree that's involved. All right, so first let me provide some background. So at a high level, computation-efficient DORAMs are based on either tree-based or square root-based ORAMs from the traditional client-server model. And so such schemes typically have sublinear computation, as you can see there in green, but they incur more bandwidth overheads than the communication-efficient DORAM counterparts. Now, the other crucial aspect that's relevant for us is that the logical RAM for n items in such schemes is in fact scrambled across a larger physical location, in particular m prime, which is strictly greater than the actual number of locations. Now, on the other hand, DORAM, being a communication-efficient DORAM, like other communication-efficient DORAMs, it incurs linear computation, as you can see there, but the advantage is it has bandwidth overheads that's logarithmic, and so better off than the computation-efficient side. Now, the crucial parts that's relevant for us is that items in DORAM, it turns out, are laid out exactly as is in the physical memory as it is in the logical RAM. And moreover, it turns out the DORAM protocol kind of allows you to access subsets of this RAM essentially for free without paying any extra overheads, which is not true of the other world. So given that, the core techniques or intuitions that underlie PRAC's efficient data structures are you can gain efficiency for data structure protocols by explicitly revealing information that would have been inherently leaked by the algorithm. And we'll see some examples of that shortly. And we can do this by exploiting this memory layout property of DORAM and its ability to allow you to operate over subsets of the RAM trivially. And furthermore, it turns out we can make this efficient in terms of the bandwidth overheads by using DPF extensions, namely incremental and wide DPFs. All right, so to give an idea of how this works, I'll describe how the oblivious binary search works at a high level. So let me start with the prior approach for binary search in the setting, which is by FlowRAM, and it uses log n DPFs to search over n items. And so the high-level idea is with each distributed point function, one selects the current pointer of the binary search from this array, perform a comparison with that item, and then update the pointer for the next part of your binary search such that you continue this log n times. Now, this protocol is clearly an overkill as it's essentially hiding each binary search pointer across these n items. But in fact, we all know a binary search access pattern has this very obvious access pattern that's induced by this binary search protocol. And so the idea is that, in fact, if you leak this particular access pattern, you're leaking no more information other than the fact that a binary search is being performed across this array. And that's exactly what we do with our binary search protocol. And moreover, it turns out this particular access pattern structure is in fact the exact same one that's induced by what is called an incremental distributed point function. So it turns out you can do all of this with just simply one distributed point function instead of logarithmically many of them. And this saves you logarithmic overhead in terms of the bandwidth, as well as logarithmic computational overheads as well. And so to quickly analytically compare our work with other approaches based for oblivious binary search, FlowRAM presents an oblivious binary search protocol with log square n, bandwidth and rounds, and n log n computation. So this arises from log n DPFs. That's where you end up with these analytics. And Raman and 3PCORAM, the computation-efficient DORAM schemes, have sublinear asymptotics, as you can kind of see there, but they pay off more in terms of bandwidth and rounds. And PRAC, in the meanwhile, has the lowest bandwidth and round complexity, just logarithmic and n directly, but they have a higher computation, in particular, they're linear. But nonetheless, as we'll see next, in concrete performance numbers, our linear computation overheads are still much better off than Raman and 3PCORAM, as they can't take advantage of these optimizations we pointed out for our protocols. So for the experimental evaluations, we use a standard setup where each party has 100 Mbps bandwidth and 30 millisecond latency each way. And PRAC and FlowRAM, in fact, have actual implementations of an oblivious binary search protocol, so we run them in its entirety and present the numbers here on this graph. The computation-efficient DORAM schemes, in fact, do not have a binary search protocol, so we estimate their costs. And I'll speak more about that shortly. But in comparison with FLORAM and 3PC ORAM, as you can see here, PRAC presents about 27 times improvements in the wall clock time, which is shown in seconds here on the y-axis. And note that this is a log-log plot, so a small gap is a large gap in theory, in practice. Now, in comparison with Raman, our protocol presents about 61 times improvements. And also, we note that this performance benefits I'm going to claim here are in fact pretty conservative because, as I said, these are estimates, but our estimates are only accounting for the DORAM accesses, the cost for initializing and pre-processing a DORAM of that particular size, as well as the cost of performing each individual DORAM access, but not the other costs involved with the other MPC operations required to perform a binary search protocol itself. Right, and finally, one last thing I'll mention here is that you can see these dashed lines for PRAC, which actually corresponds to just the online cost of running our protocol, which it turns out because PRAC is based upon DORAM, which admits an offline-online phase, wherein you just perform pre-computation in the offline phase of constructing the distributed point functions. You can gain speedups in the online phase by just utilizing them. And this gives you about another 4x factor of improvements in just the online cost it takes. In terms of bandwidth, at the same 2 to the power 26 point, PRAC presents more than 3 orders of magnitude improvements over 3PC ORAM and FLORAM, and more than 3.6 times improvements over Raman. And again, in the offline-online split, you can get another order of magnitude improvements over the improvements that I just mentioned. Now for heaps, we present a basic and optimized variant of heap insert and extract min protocols in the paper, but here I'm just going to speak a bit about our heap insert protocol, but please refer to the paper for more details on how the extract min protocols work. So at a high-level overview is that, let's say we want to insert a new item into this particular heap, and let's say this item is 13. So we create a new empty node at the next available location within this DORAM, and then this essentially fixes the path to the root from this newly inserted node, but this is a newly inserted empty node. And now, at this point in the basic version, you simply perform logging comparisons along this path to find out where this location would end up, and you leave and you place it there. But that results in a log and round complexity protocol. And so in our optimized version, we reduce this by using our binary search protocol to figure out the final location where this object would end at. And this gives you a log-log-n complexity in rounds because you're performing a binary search over this log-n path. And finally, once you do this binary search protocol, you perform an oblivious trickle-down operation with the result of this binary search protocol, which effectively leaves an empty slot for where the final location of this inserted item would be. And you complete this insertion by just doing a heap insert with an oblivious write into this particular path. And I should point out again that we can do all of this only because the underlying DORAM allows you to access just a subset of this ORAM trivially. And so we're basically leaking the fact that you're applying this heap insert on this particular path. But once again, that's leaking no more information than the fact that a heap insert is being performed along this particular path. And that's perfectly fine. And so this results in a protocol with of log-n bandwidth and of log-log-n rounds because of the binary search over that log-n size path, and a computation of log of n because your DPF is only operating over that particular path of log-n size. I'll point out that Muslim and all actually present an oblivious priority queue protocol within the malicious secure model, with it has of log square n bandwidth and rounds and computation. And unfortunately, they do not have a publicly available implementation, so we do not have experimental results against this construction. But in the paper, we provide experimental results that compare oblivious heaps with instantiations based on the other DORAMs, which our results present qualitatively similar results, just like what we saw in our binary heaps, binary search. So I won't show that here in the interest of time. Finally, I'll speak a little bit about our oblivious AVL3 protocol, but I'm not going to go into the depth of the construction here. So consider this setting where you have truly dynamic data, which needs to perform insertions and deletions and lookups over. And the natural data structure, of course, is in fact binary search trees from algorithms courses. But binary search trees have this worst case cost that's linear in the number of items you're operating over. Moreover, when you're in an oblivious setting, you in fact have to necessarily incur this linear worst case cost because otherwise you end up revealing information about the structure of this tree. And so AVL trees are a classic solution from computer science algorithm courses towards alleviating this worst case problem with binary search trees. And so in our work, we present the first AVL tree construction for the distributed trust setting where no party learns the items deleted, inserted, or searched over, all with logarithmic asymptotic complexities in terms of bandwidth and rounds. And the key challenge that really underpins this work is how do you design oblivious circuits that in fact resolve the rotation processes involved in imbalances that arise in an AVL3 protocol. And so all of that is addressed in detail within the paper, so I encourage you to check the paper out if you're interested in those details. And so to summarize, in this work, we present PRAC, a generic framework for random access computations for three-party MPC. We have new round and bandwidth efficient protocols for oblivious binary search, heaps, and AVL trees. And in the paper, we'll find more details on the algorithms for our data structure protocols, detailed experimental results, and even an evaluation for a distributed stream sampling application based on our heaps. So thank you. With that, I'm happy to take any questions you may have.
Thank you, Sachin. Do we have any questions? Oh, yeah, Mary. Yeah.
I wanted to ask about the heap protocol. When you said that it's okay to reveal the path, is that because the nodes are randomized?
No, it's kind of like saying, so let's put it this way. The tree is still secret shared, but we're basically kind of exploiting the fact that the way it's linearly laid out in memory corresponds to the underlying tree structure by the classical way. And so when you insert a new node, the fact that this is the last inserted node dictates that path, which is not controllable by anyone else, right? And so that's why it's okay to leak that particular path. All right. I see other there's.
Yeah, no, there's this one first. Go ahead.
Oh, sorry.
Yeah, I have a general question.
Yeah.
How would the framework scale for more than 3 parties? Or
So because it's based on DPFs, it really, we are using it for mostly 2 parties. The 3-party comes in for the fact that the underlying distributed ORM is a 3-party ORM, but we don't have currently any scaling mechanism for more parties at this point. We haven't considered that part of it at all.
okay, thank you.
Thanks for the talk. Maybe could you give us some intuition behind the AVL tree construction? Like, how do you know how to balance and when to balance the tree?
Right. So unfortunately, I don't have any slides on that part of it, but let me give you a very high level gist is that in the insertion case, it turns out, if you look at the AVL tree protocols, it results at most at 1 rotation at the end of the tree, more or less. And so you can perform 1 rotation over the entire tree and get away with it. And we explain in the paper how this rotation works. It turns out you can complete an imbalance rotation with, let me say you can resolve an imbalance with exactly 2 rotations. And so we always perform 2 rotations, really, right? Sometimes some of them is a fake one, but sometimes it's a real one.
Okay, so sometimes that you rotate actually you won't do anything.
Precisely.
Okay,
and sometimes you're basically not doing a rotation, but you pretend to be doing the operations involved.
Thanks.
Yeah, for sure.
Any other questions? Cool. Thanks, Jing, again.
Thank you.
So now we're going to have Gabriel, who's going to be talking about extending the security of speeds with fairness.
Thanks indeed. This is a joint work with my co-authors, Bart, Thijs, and Lisa. And you notice I'm not the first author, but Bart couldn't be here today. So I'll take the glory and honor of presenting here, together with the challenge of being the last one separating you from the end of the day and from the gala dinner. Helping me, I think this is probably going to be the least technical presentation. So hopefully I'll give a rest on your brain cells today. Let's see. Okay, so I'm going to start with some motivating example. I'm not going to be very formal here, much less formal than in the rest, but bear with me just to set the stage and to give some motivation to what we're doing. And as a motivating example, let's take, for instance, an MPC auction. Okay, so we're running an auction with MPC, and it's a very simplified auction. So we have a number of parties, 3 in the picture. We just have 1 input, so we're bidding on 1 item, and it's a single round. So their private input is the amount of money we want to bid on the item, simplified here by piles of coins. And the output we want to get is the identity of the highest bidder and the amount. So both the max and the argmax. And what you're looking at is at ways to attack this MPC protocol. Well, okay, so just to warm up, if we assume that the protocol is only secure against passive adversaries, well, essentially the sky's the limit. So, well, depending on what exactly can go wrong, many things actually could happen here if we're attacking. To begin with, if there's no check on the correctness of the output, we could enforce an incorrect output. For instance, declare we are the winner with a ridiculously low bid. Or, well, if that attack is not possible, maybe some other attacks will still be possible, like, for instance, ensuring that our input is dependent on the other one so that we can adapt our input to the other ones. Again, this is very hand-wavy, but say the point that I'm trying to make here is that there are, say, intended applications for MPC where you do want to look into active security, where arguably you do want to look into protocols that are secure against a dishonest, actively dishonest attacker. Okay, so, well, and much more. Okay, so let's say, okay, then we're going to focus on actively secure protocols. So like the attacks as before should not work now. But that might not be the end of the day. So you might still be able to actually sort of like attack to make the essentially the auction useless, or say to break the validity of the auction while still being compliant with an actively secure protocol. And the reason is that some, for instance, this MPC protocol might be secure against active attackers, but might only offer security with selective abort, which means, okay, parties will not accept an incorrect result, but they might just still like block abort. And as an attacker, you might be able to learn the correct result. So what you can do is, well, you start with some, well, say a very low bit. You learn the output of a computation, so the highest bit, who will have won, but you leave the protocol to abort. So at that point, nobody else has this information, but you do have this valuable information. Okay, what was the value you will need to win? And then if you execute the protocol again, or if the auction continues on the same item, you can just bid a little bit more and be sure to be a winner. So you have a really unfair advantage in this case. And again, this can actually happen. So it's a little bit less hand-wavy than the previous slide, because this can happen. So this is something which can happen in actively secure MPC protocols which are deployed, which are very popular nowadays. More in general, let's say, so you can actually conceive situations where it can be interesting for an attacker to get the asymmetric knowledge, so to be the only one to know the output of a computation. So just to give one example, I think I'm going to skip on the second one. If you look at benchmarking, one proposed application MPC is in financial benchmark between companies. Well, it would be very interesting if you could be the only one to get the benchmarking of you and your competitors while preventing the other ones to get the same result. So there are situations where actually it might be interesting for an attacker to be the only one to get the result. And the thing is that a priori, if you have an actively secure MPC protocol which only offers security with selective abort, there's no guarantee that this attack will fail, and actually they might succeed. And in particular, speeds, which you've seen before in a couple of presentations, it offers no security that can prevent these attacks, and actually can be very easily attacked, because in general, speeds follow the structure revealing the output, which we could call here reveal, check, and then produce the output. And it's very easy to carry on such an attack on that. Okay, so let's see what have we been doing about that. Well, it is that we extend speeds, so we do focus on speeds. It's not on the generic class of security with abort protocols, and we're extending in such a way that, well, we retain the same security guarantees for an unbounded number of adversaries. So if the corruption is up to n, just smaller than n, we get the same security with abort. But if we have an honest majority, so if less than half of the players are corrupted, then we also get fairness, which means that either everybody will get the outcome of a computation or nobody will get it. And the thing is, well, we cannot actually do more than half of corrupted play in this setting, so this is pretty much optimal. And also, like, one important thing is that we do not need to know the number of corruptions, so it doesn't need to be an input in the protocol. And well, you see, like with the overhead, this at speed is actually fairly minimal. Plus, if you're interested, you can refer to the paper for security proofs, implementation, benchmarking, etc. Okay, I'm gonna dash through what we have been doing. Disclaimer here, so I'm not gonna present exactly what we've been doing. I'm gonna present a slightly more general version, which is simpler. So again, trying to give a rest to your poor brain cells, which is almost 5 p.m. So what we need is a bit more specific to speeds, a bit more, so it's complex and more specific to speeds, also to improve efficiency. Also, other upside of this presentation, it's a bit more generic, so you can see it not only valid for speeds. But okay, so I guess I can go very fast through this recap of speed, because we've seen before in the presentation from Sebastian. Just to spice things up, I'm using a different notation. So here, Sebastian was using double brackets for secret share values with the associated MAC tags. I'm using the curly brackets. But essentially, well, just very fast recap. How does speeds work? So you secret share your element, you'll obtain some tags on it, you'll perform a computation over secret shares, and then you reveal. Interesting part for us is how you reveal the output. So how do you pursue this? Well, first you will reconstruct the supposed output values, so not touching the tags for now. And then you will actually check that the tag check is valid. So you will subtract the tag times, you will subtract from the tag the output value times the MAC keys, and you'll check that that is equal to 0. If it is equal to 0, then you're happy. Okay, that's the output. And if not, you abort, fail. Some cheating has occurred. Well, to make things a bit more concrete, as I said, you can attack this very easily if you want to steal the result, let's say, and maybe you saw it yourself. Because here the thing is that, okay, we share the input values, we compute them, then we reveal them, we check that the output is correct, and if it is, okay, that's the real output. So what an attacker can do, they can just carry on like behaving honestly till the output is revealed, then cheat during the tag check. At that point, the honest party will not accept the output, but you as an attacker, you know that that was the correct output. So essentially, nobody else gets it. We only get a partial result, which you cannot use. There's no guarantee that's correct, but you do get it, and you do know that it's right. And here also, like, interesting point towards where I'm gonna go is that the crucial part is really very revealing, and indeed the nice part of our construction, in my opinion, is that we mostly essentially touch only the revealing phase. So the computation and so on goes on just as usual. We just touch the revealing phase. Okay, and so what are we doing again in a slightly more generic and simplified constructions? Okay, so assume that you have a protocol that allows you to reconstruct a secret share value B, secret sharing the same way as, say, speeds or as the protocol you're using. So it is not an MPC protocol, right? It just allows you to reconstruct, no computation on it, but you reconstruct with fairness if the regime parameters allows that. And then what you can do is simply that you use speeds, not to compute the actual output f of x, but to compute f of x plus a random value b. So at this point, you do not have fairness on this protocol, but it doesn't matter, because even if an attacker tries to steal the result, they're only going to steal the mask result, so f of x plus random value, so we don't get anything out of it. And then you can actually securely reconstruct b with fairness, if the regime of parameters allows for that. And then you'll subtract from y, and you get the result. So concretely in our protocol, well, to realize this fair reconstruction, we use a conversion to Shamir sharing. And as I said, actually what we do is a bit more involved because we leverage a little bit more of a structural speeds for efficiency. In particular, we also use the tag checks of speeds to ensure this conversion is performed in the right way. And we can push some of the things to be a pre-processing phase of speeds. Okay, well, so we do that. The nice part, again, so we only touch essentially the reconstruction phase, which means that the overhead is typically very, very small. So here it's an example of running a circuit for a neural network evaluation. And what you see is the overhead, so the difference. And see it's very, very small, which at this point should not be that surprising because we're not really touching the evaluation of a function, right? So running through the circuit, that's going to go exactly the same way. So you have zero overhead. Just what you have is you have to create a little bit more checking values in the preprocessing phase, and the revealing phase is a bit more involved, but not even that much. Okay, for conclusion, I think I'm going to be very fast because actually, I mean, it's just summing up what you've seen in the last 5 minutes, so hopefully you'll still remember what's in there. But so we extended speeds to achieve fairness if the regime of parameters allows that, and we have sort of like graceful system where you do not need to know how many parties are corrupt. With a minimal overhead. Well, I'm also listing here some possible future work, but well, we can expand if you want on that on the during the questions. So with that, I think I can conclude. Thank you.
Thank you, Gabriela. Do we have any questions? No?
Yeah. So one of the selling arguments of speeds is, of course, the security for dishonest majority, or in presence of a dishonest majority. And here with this construction, at first, I would intuitively assume that the
protocol where you reconstruct B is no longer secure in presence of a dishonest majority because it uses Shamir secret sharing. So how can you explain this?
Yes, so the thing is that for correctness, which speeds indeed guarantees also for a dishonest majority, we are still relying on the MAC check. So we're not only just converting to Shamir and that's it and forgetting about the MACs, we are still making use of these MACs. So both when computing Y and then when we ensure the reconstruction to B.
So your correct reconstruction of B is still subject to a MAC check or something? Because if you tamper with B, then you have tampered with the output, right?
Exactly. So essentially, we use the MACs to ensure that you will be we check the text on B, and then we ensure that the value you're opening has the same tags. So is the same one as we check the tags of. Hope that gives some idea.
Yeah, I guess to understand it fully, I would probably need to read the paper, but it's good to know.
Next question.
Yeah. So do you think your ideas apply to like any kind of MPC protocol that uses MACs? Maybe slightly related to the previous question, but like, I don't know, any like honest majority protocol that uses MACs, or maybe like a dishonest majority protocol that uses packed secret sharing with MACs, anything like this?
I will say in this form I'm presenting here, I will guess yes. Again, what we're doing is a bit more tailored to speed, so there will need some tweaking to be generalized. That being said, yeah, so I will say yes, but then from there to writing a full security proof is a long story. So that would be my guess.
Can you hear me?
So I think we have a question on Zoom. Yeah.
Can you hear me?
Yep.
Great. So also on this slide, at the top, if you have a protocol that given a sharing of a value can reconstruct that value with fairness and security, why don't you just apply that protocol directly to the sharing of f at x? Why do you need this blinding value?
Well, a couple of reasons. One thing is that in this way we can push the creation of these blinding and the auxiliary materials for the conversion to the preprocessing phase of speeds. And also, I think if we will do that directly and we have a dishonest majority, I think that will violate fairness, because at this point, so for a dishonest majority, parties can reconstruct the no, what am I saying? Yeah, sorry, I'm getting tangled up. But I think there was also a security reason to do that. I'll need to think about it with a fresher mind.
Okay, thanks.
Okay, let's thank Gabriele again and all the speakers from the session. Thank you, and this ends the MPC session.